Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the deep cosmos where black holes first learned to exist. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. In the universe's first few 100 million years, darkness stretches across space like a slow, cosmic exhale that has lasted longer than Earth will ever exist. No stars shine yet in this primordial void. No galaxies spiral through the emptiness with their elegant arms of light and dust. No planets orbit warming suns. No moons cast silver shadows across alien landscapes. Only hydrogen and helium drift in vast, cooling clouds, remnants of the Big Bang's initial fire, now spread thin across distances that dwarf human comprehension like grains of sand scattered across an infinite beach. The cosmos measures its age not in human lifespans, not in the rise and fall of civilizations, not even in the slow erosion of mountains or the patient drift of continents, but in the imperceptible accumulation of gas, atom by wandering atom, into the first stellar nurseries. Time moves differently here, in units so vast that entire geological epochs would pass unnoticed, like seconds ticking by on some impossible cosmic clock that measures eternity in the gentle dance of gravitational attraction. These primordial clouds possess a quality that later generations of stars will never know again. Perfect chemical simplicity that speaks to the universe's innocent youth. No carbon forged in stellar cores through the triple alpha process. No oxygen destined to fill alien atmospheres or flow through the bloodstreams of creatures not yet dreamed. No silicon waiting to form the rocky foundations of terrestrial worlds. No iron that will one day flow red through landscapes under foreign suns. Only the universe's original elements, hydrogen and helium, pure and unadorned as the first snow falling on an empty world, gathering under their own gentle gravitational pull with the persistence of water finding its level across cosmic distances. The temperature of space itself hovers just a few degrees above absolute zero, filled with the afterglow of creation. The cosmic microwave background radiation that bathes everything in its ancient, invisible warmth. This radiation carries within its subtle variations the fingerprints of the universe's earliest moments, tiny fluctuations in density that will eventually grow into the largest structures the cosmos will ever know. Scientists studying this primordial light can map the seeds of galaxy clusters and cosmic voids with the precision of archaeologists uncovering artifacts from civilization's dawn. The gas falls inward with the inevitability of autumn leaves settling to Earth, but across timescales that stretch beyond human imagination like an ocean of years. 1,000,000 years passes in what feels like a single breath. 10 million years flow by like water over stones. 100 million years accumulate like sediment in some vast temporal river. The clouds contract by degrees so subtle that no conceivable instrument could detect the change from moment to moment. Yet gravity never rests, never pauses in its quiet, relentless work. Each hydrogen atom draws its neighbors closer with forces so gentle they barely disturb the cosmic microwave background radiation, yet so persistent they reshape the architecture of space itself. The mathematics governing this process unfold according to Newton's inverse square law, gravitational attraction weakening with distance, but never disappearing entirely. Every particle in the universe pulls on every other particle with forces that diminish but never cease, creating an invisible web of influence that connects the smallest atom to the most distant galaxy. Here, in this primordial darkness that predates the formation of our solar system by billions of years, that existed when the Milky Way was nothing more than a slight overdensity in the cosmic web, something unprecedented begins to stir with the patience of geological processes. The first massive stars, population 3 giants that modern astronomy knows only through theoretical models and computer simulations, start their formation process in these hydrogen havens, like seeds beginning to sprout in fertile darkness. These stellar pioneers grow enormous by the standards of any star that has existed since, sometimes reaching masses 200, 300, even 400 times greater than our Sun. Such massive objects seem almost impossible by contemporary standards. Stellar monsters that challenge our understanding of how matter can organize itself in the early universe. They will burn bright and brief when their time comes, like cosmic matches struck in an infinite cathedral where no sound travels, no witness observes, and time itself moves to rhythms unknown to smaller, more familiar worlds. The formation process unfolds with exquisite slowness, following physical laws that operate across scales from the quantum to the cosmic. As the primordial gas clouds continue their gravitational collapse, their centers begin to warm through a process as inevitable as dawn following night. The potential energy of position, each gas particle suspended in the cloud's gravitational well, converts gradually to kinetic energy of motion as particles fall inward, then to thermal energy through countless gentle collisions that occur like raindrops on a vast pond. The temperature climbs degree by patient degree, following thermodynamic principles that govern everything from cooling coffee to the life cycles of stars. What begins at just a few degrees above absolute zero slowly warms to hundreds, then thousands of degrees as gravitational potential energy transforms into heat. The process spans millions of years, each increment of warming earned through eons of compression, like some cosmic engine converting space into time, mass into energy, darkness into the promise of light. Scientists studying the cosmic microwave background radiation can still detect the faint echoes of density fluctuations from this era, tiny variations in temperature that correspond to regions where matter began clustering more densely than the cosmic average. These fluctuations, measured at just a few parts per million, represent the seeds from which all cosmic structure would eventually grow. Galaxies, star clusters, planetary systems, and ultimately, life itself trace their origins back to these almost imperceptible variations in the early universe's otherwise smooth distribution of matter and energy. The gene's length, that critical size at which a gas cloud becomes gravitationally unstable, determines whether a region of space will birth stars or remain forever empty like vast cosmic deserts between oases of light. This fundamental scale emerges from the eternal competition between thermal pressure pushing outward and gravitational attraction pulling inward. Two forces locked in a delicate balance that determines the fate of matter across the universe. The irony whispers itself across the void with the subtlety of starlight reflecting on still water. These first stars, destined to become the universe's first black holes, will shine with a fierce brilliance that later generations of stars will never equal. Their nuclear fires will rage at temperatures and pressures unknown to smaller, longer-lived stars, consuming their hydrogen fuel with reckless abandon like cosmic bonfires burning through forests of primordial gas. Yet even as these giants prepare to blaze across the darkness, they carry within their forming cores the seeds of their own inevitable transformation. The same gravity that draws them together from the cosmic dark will eventually become their undoing, their final destiny. Their massive hearts grow denser with each passing eon, accumulating the very conditions that will eventually trigger their spectacular collapse into regions of space-time so severely warped that not even light itself can escape their gravitational embrace. Computer models running on the most powerful supercomputers suggest these first stars reached masses that seem almost impossible by modern stellar standards, stellar monsters that burned so hot they barely held themselves together through their brief, brilliant lifetimes. Only took a few million years for them to exhaust their nuclear fuel reserves. A cosmic eye blink compared to the billions of years that smaller stars like our Sun will enjoy in their steady, patient burning. The universe watches and waits as these stellar nurseries continue their slow, inevitable work across the darkness. Each cloud collapses at its own patient pace, following physical laws that will govern star formation for the next 13 billion years and beyond, until the last red dwarf burns out in a cosmos grown cold and thin. The process unfolds with the rhythm of deep time, imperceptible moment by imperceptible moment, millennium by quiet millennium, until suddenly, inevitably, nuclear ignition begins and the cosmos experiences its first dawn breaking across the infinite night. And in that approaching first light, still millions of years in the future, the universe glimpses its own destiny with the clarity of prophecy written in equations and physical law. These massive stars will live fast, die spectacularly, and leave behind gravitational monsters that will shape the architecture of every galaxy yet to come. Every structure that will ever form in the cosmic web of matter and energy, stretching across space and time, the moment arrives not with fanfare, but with the quiet inevitability of seasons turning on some unimaginably distant world, deep within the core of a population 3 giant. Temperatures climb past 10 million degrees Kelvin with the patience of geological processes, and hydrogen nuclei overcome their mutual electrical repulsion to fuse into helium for the first time in cosmic history. Nuclear fire ignites in the heart of darkness, and the universe experiences its inaugural dawn, a solitary star blazing alone in an ocean of emptiness that stretches beyond the capacity of human imagination to grasp. This first stellar furnace burns with an intensity that seems almost violent compared to the gentle, steady stars that will follow billions of years later. The core temperature soars past 100 million degrees Kelvin, climbing toward temperatures 50 times hotter than the center of our Sun, creating conditions so extreme that matter exists in states unknown anywhere in the modern universe. Hydrogen fuses into helium at rates that consume the star's fuel reserves with breathtaking speed, like some cosmic engine running at maximum throttle with no thought for tomorrow, no concern for the finite nature of its nuclear reserves. The energy released through Einstein's mass-energy conversion travels outward through layers of stellar material in a journey that spans thousands of years. Photons created in the nuclear furnace of the core undergo countless absorptions and re-emissions as they migrate through the stellar interior, each interaction changing their wavelength and direction in a random walk that eventually carries them to the surface. What begins as high-energy gamma radiation emerges as visible light and heat, finally escaping into the waiting darkness after millennia of imprisonment within the star's own material. The star's photosphere glows blue-white, with surface temperatures reaching 40,000 degrees Kelvin, radiating energy across the entire electromagnetic spectrum with particular intensity in the ultraviolet range. This harsh radiation begins the universe's first phase of reionization, stripping electrons from hydrogen atoms across vast spherical volumes of space that expand outward at the speed of light. What was once neutral gas, hydrogen atoms with their electrons bound in tidy quantum orbits, becomes a plasma of free protons and electrons, transforming the cosmos from electrically neutral to ionized, from opaque to transparent to its own light. The ionization process occurs gradually, bubble by expanding bubble, as ultraviolet photons race outward from the stellar surface, carrying energy sufficient to break the bonds that hold electrons to protons. Each photon can ionize one hydrogen atom before being absorbed, but the newly ionized gas also begins emitting its own radiation as free electrons recombine with protons, creating a complex web of radiative processes that operate across scales from atomic to galactic. The star's influence spreads across distances measured in hundreds of light years, carving out ever larger cavities of ionized gas in the neutral hydrogen that fills most of space. Within the stellar core, fusion proceeds through the proton-proton chain reaction, the same nuclear pathway that will power main sequence stars for billions of years to come. 4 hydrogen nuclei combine through a series of intermediate steps involving positrons, neutrinos, and gamma rays to form one helium nucleus, releasing energy according to Einstein's famous mass-energy equivalence. The difference in mass between 4 hydrogen atoms and 1 helium atom, just 0.7%, becomes pure energy through the most celebrated equation in physics, E=mc². Yet the star's enormous mass drives fusion at rates that seem almost frantic compared to smaller stars, where our Sun converts roughly 4 million tons of matter to energy each second through nuclear reactions. These primordial giants consume their hydrogen reserves hundreds of times faster, burning through their fuel like cosmic bonfires, consuming entire forests of gas and dust. The stellar interior becomes a furnace of such extraordinary intensity that exotic nuclear processes begin occurring alongside the standard proton-proton reactions that dominate in smaller stars. Core temperatures climb so high that even helium nuclei start fusing together through the triple alpha process, a delicate nuclear reaction that combines 3 helium-4 nuclei in rapid succession to form carbon-12. This reaction requires temperatures exceeding 100 million degrees Kelvin and occurs through a quantum mechanical resonance discovered by Fred Hoyle, a precise energy level in the carbon-12 nucleus that makes the reaction possible. Without this resonance, carbon formation would be extremely rare, and the universe might never have developed the chemical complexity necessary for life. The formation of carbon through helium burning represents the universe's first step toward chemical enrichment, the gradual construction of a periodic table that began with only hydrogen and helium. Oxygen forms through additional alpha captures onto carbon nuclei, while neon, magnesium, and silicon arise through further fusion processes as core temperatures continue climbing. Each successive burning phase requires higher temperatures and produces less energy per unit mass, driving the star through an accelerating sequence of nuclear transformations. Only took a few million years for the hydrogen in the core to become completely exhausted, transformed entirely into helium and heavier elements through the relentless furnace of nuclear fusion. This represents perhaps the universe's first great cosmic irony, the most massive stars, blessed with the largest fuel reserves, burn out fastest of all. Their enormous gravitational pressure drives nuclear reactions at such extreme rates that longevity becomes impossible. They trade duration for intensity, burning bright enough to outshine entire future galaxies while living briefer lives than some of Earth's geological formations. As hydrogen depletion approaches, the star begins experiencing internal structural changes that will ultimately seal its fate. The nuclear fires in the core start to dim as fuel runs low, reducing the outward radiation pressure that has balanced gravitational collapse for millions of years. Without this support, the core contracts under its own immense weight, growing denser and hotter as gravitational potential energy converts to thermal energy through the compression of stellar material. This gravitational contraction ignites helium fusion in the core, causing temperatures to spike even higher as helium nuclei overcome their electrical repulsion to fuse into carbon and oxygen. The energy release temporarily halts the core's collapse, but the helium fuel burns even faster than hydrogen due to the higher temperatures required for fusion. Meanwhile, a shell of hydrogen continues burning around the inert helium core, creating a complex internal structure where multiple fusion processes operate simultaneously at different radii within the star. The process creates an onion shell architecture within the stellar interior, a carbon-oxygen core surrounded by a helium-burning shell, surrounded by a hydrogen-burning shell, all wrapped in layers of unburned hydrogen that extend outward to the star's photosphere. Each shell burns its nuclear fuel at temperatures and pressures determined by the total weight of material pressing down from above, following hydrostatic equilibrium conditions that balance gravitational compression against radiation pressure. Advanced computer simulations reveal that the most massive population 3 stars develop additional burning shells as core contraction continues. Carbon burning produces neon and magnesium at temperatures exceeding 600 million degrees Kelvin. Neon burning creates oxygen and magnesium at temperatures above 1 billion degrees. Oxygen burning forms silicon, sulfur, and other intermediate mass elements at temperatures approaching 2 billion degrees. Each successive phase lasts for shorter periods as the energy release per fusion reaction decreases while the energy requirements for ignition increase. Scientists still debate exactly how these first stars ended their lives. Since no direct observational evidence exists from such ancient cosmic epochs, theoretical models and computer simulations suggest that stars above a certain mass threshold, perhaps 150 solar masses, experience a fundamentally different kind of death than the core collapse supernovae that modern astronomy regularly observes. Instead of exploding outward in spectacular blasts that scatter heavy elements across space, the most massive population 3 stars may have collapsed directly into black holes, swallowing their newly forged elements without ever releasing them to enrich the surrounding cosmos. The exact mass boundary for direct collapse versus explosive disruption remains one of modern astrophysics' most elegant unsolved puzzles. Below this critical threshold, stars explode as pair instability supernovae, thermonuclear detonations so powerful they completely destroy the star, dispersing all its material into space and leaving no compact remnant behind. Above this threshold, the star's core becomes so dense and hot that not even the tremendous energy release of nuclear burning can halt gravitational collapse. The star simply falls inward upon itself, disappearing behind an event horizon from which no information can ever return to the outside universe. As the stellar core continues burning progressively heavier elements, carbon fusing into neon, neon into magnesium, magnesium into silicon, each successive fusion stage releases less energy per unit mass while requiring exponentially higher temperatures to proceed. The star races through these final burning phases with increasing desperation, like a mountain climber ascending peaks where each step demands more effort while providing less oxygen. Silicon burning. The ultimate nuclear process before gravitational collapse lasts only days or weeks in these massive stars. Compared to the millions of years they spent converting hydrogen into helium, the end approaches with mathematical precision dictated by nuclear physics and quantum mechanics. When the core temperature reaches 3 billion degrees Kelvin, our silicon nuclei begin fusing together through a complex network of reactions that build progressively heavier elements. But this process leads inevitably toward iron 56, the most tightly bound nucleus in nature and the peak of nuclear stability. Iron cannot release energy through either fission into lighter elements or fusion into heavier ones. It represents the thermodynamic endpoint of nuclear burning. When the stellar core becomes predominantly iron, nuclear energy generation stops entirely for the first time since the star began shining millions of years earlier. Gravitational collapse proceeds unimpeded, compressing matter to densities that exceed those found in atomic nuclei in less than a second. The core density increases by factors of trillions, from roughly the density of water to conditions where protons and neutrons touch each other directly. The collapse generates temperatures exceeding 100 billion degrees Kelvin, hot enough to photodisintegrate iron nuclei back into individual protons and neutrons. At this moment of ultimate gravitational triumph, the universe prepares to witness its first black hole formation through stellar collapse, not through gradual accretion or slow evolution, but through the catastrophic implosion of a star whose mass exceeds all limits that the physics of matter can support. The stellar remnant crashes through neutron degeneracy pressure, the final quantum mechanical barrier against gravitational compression, creating a singularity surrounded by an event horizon from which not even light can escape. The black hole's formation marks the universe's first encounter with regions of space-time curved so severely that they form gravitational traps of infinite depth. General relativity predicts that matter, falling past the event horizon, continues collapsing toward a mathematical point of infinite density and zero volume, a singularity where the known laws of physics break down and space and time themselves cease to have meaning in any conventional sense. Only took 10 million years from first nuclear ignition to final gravitational collapse, and the cosmos gains its first permanent resident, an object destined to outlive every star, every planet, every galaxy that will ever form during the next trillions of years of cosmic evolution. The irony echoes across the expanding void with the clarity of prophecy. The universe's brightest early beacon creates its first region of eternal darkness, beginning a story of gravitational monsters that will continue long after the last red dwarf star burns out in a cosmos grown cold, thin, and empty. The universe now possesses its first black hole, but this stellar mass remnant represents merely the smallest member of a family that will eventually span 9 orders of magnitude in size, from objects barely more massive than mountains to gravitational monsters exceeding the mass of 10 billion suns. Across the cosmos, during these same early epochs when the first stars are dying in spectacular gravitational collapse, other mechanisms begin planting the seeds for supermassive black holes, objects so massive they will anchor entire galaxies around their invisible presence, like cosmic lighthouses marking vast territories in the primordial dark. The formation pathways for these supermassive seeds remain among the most elegant and perplexing puzzles in modern theoretical astrophysics, challenging our understanding of how matter can organize itself during the universe's youth. Computer simulations running on the world's most powerful supercomputers reveal multiple routes through which the early cosmos might have assembled such staggeringly massive objects before the first billion years had elapsed since the Big Bang. Each pathway requires precise initial conditions and delicate balances between competing physical processes that operate across scales from quantum mechanical to galactic. Direct collapse scenarios represent perhaps the most dramatic route towards supermassive black hole formation. Envisioning pristine gas clouds with masses reaching hundreds of thousands of times that of our Sun falling inward under their own gravity without ever fragmenting into individual stars. These clouds must accumulate mass continuously through smooth, uninterrupted accretion until they reach sufficient density to collapse directly into massive black holes before nuclear ignition can disrupt the process through stellar winds and radiation pressure. The physical conditions required for direct collapse exist only during narrow windows in cosmic history, when the universe possessed the precise combination of temperature, density, and chemical composition necessary to prevent star formation while allowing gravitational collapse. The gas must remain at temperatures near 10,000 degrees Kelvin, hot enough to provide sufficient thermal pressure to prevent fragmentation into smaller clumps, but cool enough to allow the overall gravitational collapse of the cloud as a coherent structure. Molecular hydrogen, which normally provides crucial cooling through its rotational and vibrational energy states, must be systematically suppressed by external radiation fields that photodissociate the molecules as quickly as they form. This creates a delicate chemical balance where the gas remains in its atomic state, individual hydrogen and helium atoms, rather than forming the molecular species that would normally trigger rapid cooling and subsequent fragmentation into star-forming cores. The chemistry involved reads like a cosmic recipe written in the fundamental language of quantum mechanics and statistical thermodynamics. Trace amounts of molecular hydrogen form through rare three-body collisions between hydrogen atoms, reactions that occur perhaps once per cubic meter per year in these tenuous primordial clouds drifting through the early universe. Each collision requires precise alignments of atomic velocities and quantum energy states, making molecular formation an intrinsically inefficient process in the low-density conditions of early cosmic gas. Yet even this tiny concentration of H2 molecules, perhaps 1 molecule per million hydrogen atoms, can provide enough cooling through rotational transitions to trigger fragmentation into smaller, star-forming clumps that would disrupt the direct collapse process. Nearby sources of ultraviolet radiation, perhaps the first generation of massive stars burning in adjacent regions of space, must continuously photodissociate these molecules as quickly as they form through chemical reactions, maintaining the gas cloud in its pristine, atomic state for millions of years. The Lyman-Werner radiation band, spanning photon energies from 11.2 to 13.6 electron volts, proves particularly effective at destroying molecular hydrogen without ionizing the atomic hydrogen that comprises most of the cloud's mass. This creates a feedback mechanism where the first generation of stars regulates the formation of supermassive black hole seeds through their ultraviolet emission, demonstrating how stellar and black hole formation processes remain intimately connected during the universe's earliest epochs. Alternative formation scenarios invoke intermediate mass black holes as stepping stones towards supermassive growth, suggesting that dense stellar clusters in the early universe might have undergone runaway merger processes, where the most massive stars sink toward the cluster center through dynamical friction. These stellar collisions could build black holes with masses reaching 10,000 to 100,000 solar masses before tidal disruption and stellar evolution processes disperse the parent cluster, creating seeds large enough to grow efficiently into supermassive objects through subsequent accretion of surrounding gas. The dynamics of these primordial stellar clusters operate according to gravitational n-body physics that creates natural mass segregation, where the most massive objects spiral inward while lighter stars migrate to larger orbital radii. This process, known as equipartition of energy, occurs through gravitational encounters between cluster members that gradually redistribute kinetic energy until the most massive stars occupy the deepest regions of the cluster's gravitational potential well. Stellar collision rates in these dense environments can exceed 1 per 1,000 years, orders of magnitude higher than collision rates in modern globular clusters. Each collision merges 2 stars into a single, more massive object that becomes even more likely to experience additional collisions as it continues sinking toward the cluster center. The process creates a runaway growth mechanism where intermediate mass black holes can form and grow rapidly before the cluster disperses through internal dynamics or external tidal forces. The timescales involved in growing from intermediate mass seeds to supermassive black holes stretch across hundreds of millions of years, during which these embryonic gravitational monsters must compete with stellar feedback processes and galaxy formation dynamics that can disrupt their feeding patterns. Theoretical models suggest growth rates fundamentally limited by the Eddington luminosity, the precise balance point where outward radiation pressure from infalling matter exactly counteracts inward gravitational attraction. A black hole attempting to accrete matter faster than the Eddington rate would generate so much luminosity from the heating and compression of infalling gas that the radiation pressure would blow away its fuel supply, creating a self-regulating feedback mechanism that prevents unlimited growth. The Eddington luminosity scales directly with black hole mass, meaning that more massive seeds can grow faster in absolute terms while maintaining the same efficiency of mass-to-light conversion through gravitational potential energy release. Yet observations of high redshift quasars reveal supermassive black holes with masses exceeding 10 billion solar masses existing when the universe was less than 700 million years old, barely 5% of its current age. These ancient giants challenge theoretical understanding through their very existence, requiring sustained growth at or near the Eddington limit for hundreds of millions of years, or alternatively demanding seed masses much larger than stellar remnants or intermediate mass black holes could reasonably provide. The mystery deepens when considering that these early supermassive black holes appear to have grown in environments where gas densities were higher and galaxy merger rates more frequent than in the modern universe. Gas-rich protogalaxies colliding and merging during cosmic dawn could have triggered massive inflow episodes that fed central black holes through gravitational torques and tidal streams, creating conditions where rapid growth becomes not only possible, but inevitable. Only took a few 100 million years for these seeds to reach masses comparable to the central black holes in modern massive galaxies like our own Milky Way, representing growth rates that push theoretical models to their absolute limits. The universe during this epoch resembled a vast cosmic construction site, with gas-rich galaxies merging frequently in the dense environment of the early cosmic web, feeding their central black holes through processes that operate across scales from stellar to galactic and beyond. Primordial black holes represent yet another pathway toward massive seed formation, though their existence remains entirely hypothetical and depends on conditions during the universe's first moments that may never have actually occurred. These exotic objects would have formed directly from density fluctuations during cosmic inflation, collapsing under their own gravity during the first seconds or minutes after the Big Bang, long before the first stars ignited or the first galaxies began assembling from dark matter and baryonic gas. The quantum physics governing primordial black hole formation operates according to principles that seem almost mystical in their mathematical elegance and precision. Regions where the density exceeded the cosmic average by more than a critical threshold, roughly 50% during the radiation-dominated epoch, would decouple from the general expansion of space and undergo gravitational collapse into black holes whose masses depend on the horizon scale at the time of formation. The horizon scale represents roughly the maximum distance that light could have traveled since the Big Bang began, defining a fundamental length scale that grows with cosmic time as the universe ages and expands. During the first microsecond after the Big Bang, the horizon scale corresponded to masses smaller than asteroids. By 1 second, horizon scale masses had grown to roughly the mass of our Sun. By 1 minute, horizon masses reached thousands of solar masses, potentially providing seeds massive enough to grow into the supermassive black holes observed in high redshift quasars. These primordial seeds, if they exist in nature rather than merely in theoretical calculations, would possess masses distributed across a broad spectrum determined by the statistical properties of primordial density fluctuations imprinted during cosmic inflation. Most would be microscopic, with masses comparable to mountains or asteroids, but rare peaks in the primordial density field could produce black holes with stellar or even supermassive scale masses during the universe's first moments. The cosmic web itself participates actively in this seeding process. Channeling gas flows along filamentary structures that connect dark matter halos across the universe like a vast three-dimensional spiderweb of matter and energy. Baryonic gas streaming along these cosmic filaments encounters turbulent mixing, shock heating, and gravitational focusing that can either promote or inhibit black hole formation, depending on the precise balance of competing physical processes operating across multiple decades in spatial and temporal scales. Dark matter halos provide the gravitational scaffolding that collects baryonic matter from the cosmic web, creating overdense regions where black hole seeds can form through direct collapse. Stellar cluster dynamics, or primordial fluctuations. The relationship between dark matter halo mass and central black hole mass, established during these early epochs, may explain the tight correlations observed between supermassive black holes and their host galaxy properties in the modern universe. Modern astronomical observations reveal that virtually every massive galaxy harbors a supermassive black hole at its center, with masses that correlate remarkably tightly with properties of the host galaxy's central stellar bulge. The relationship between black hole mass and bulge velocity dispersion, known as the M-sigma relation, suggests a fundamental connection between black hole growth and galaxy formation that operates consistently across cosmic time, from the earliest quasars to nearby elliptical galaxies. This correlation implies that the universe somehow coordinates the assembly of these vastly different galactic components, stellar populations comprising billions of individual stars and invisible gravitational monsters more massive than entire star clusters, through feedback mechanisms that operate across enormous ranges in spatial and temporal scales. Galaxy mergers trigger gravitational torques that drive gas inflows towards central black holes, while black hole accretion generates powerful outflows of relativistic particles and electromagnetic radiation that regulate star formation rates across entire galactic disks. The mystery deepens when considering that supermassive black holes typically contain only about 0.1% of their host galaxy's total stellar mass. Yet, their growth histories remain mysteriously synchronized across billions of years of cosmic evolution. This suggests feedback processes so precisely calibrated that black hole and stellar mass growth rates remain proportional despite operating through completely different physical mechanisms, gravitational accretion versus nuclear fusion, across vastly different spatial scales. Only took the universe its first billion years to establish the population of supermassive black holes that will dominate galactic evolution for the remainder of cosmic history. Seeding every major galaxy with a central gravitational engine capable of outshining all the galaxy's hundreds of billions of stars combined when actively feeding on surrounding matter. The cosmic irony whispers across deep time with the subtlety of quantum mechanics. These seeds of gravitational darkness become the universe's brightest beacons when feeding, marking the locations of distant galaxies across such vast distances that their light requires billions of years to traverse the expanding cosmos. Carrying encoded information about cosmic dawn in the spectral signatures of ancient starlight redshifted by universal expansion. Around these newly formed black holes, whether stellar remnants or supermassive seeds, the universe begins composing its first accretion disk symphonies, vast spiraling structures of gas and dust that transform gravitational potential energy into electromagnetic radiation through processes so fundamental they will persist unchanged for the next 13 billion years. Matter falling toward a black hole cannot simply plunge straight inward due to conservation of angular momentum, the same physical principle that causes figure skaters to spin faster when they pull their arms inward during pirouettes. Instead, infalling material must spiral gradually closer through a series of nearly circular orbits, shedding angular momentum through viscous friction and magnetic field interactions that operate on timescales ranging from thousands to millions of years. This creates accretion disks, flattened structures of rotating matter that can extend from just outside the black hole's event horizon to distances comparable to our solar system, with internal temperatures and pressures that rival conditions inside stellar cores. The physics governing these accretion flows combines elements from fluid dynamics, plasma physics, magnetohydrodynamics, and general relativity into mathematical frameworks so complex that even modern supercomputers struggle to simulate them accurately. Viscosity within the disk arises not from molecular collisions, as in everyday fluids, but from turbulent magnetic field instabilities that transport angular momentum outward while allowing matter to migrate inward toward the black hole's gravitational embrace. Gas entering the accretion disk carries kinetic energy corresponding to its orbital motion around the central black hole. Energy that must be dissipated as the material spirals inward to smaller orbital radii. This energy dissipation occurs through friction between adjacent annuli of rotating gas, converting ordered orbital motion into random thermal motion that heats the disk material to temperatures exceeding millions of degrees Kelvin in the innermost regions. The temperature profile follows a precise mathematical relationship derived from the balance between gravitational heating and radiative cooling, creating a disk structure where the hottest material orbits closest to the event horizon while cooler gas extends outward to larger radii. Near a stellar mass black hole, the inner edge of the accretion disk reaches temperatures comparable to those found in stellar cores, hot enough to ionize any atoms and create a plasma of free electrons and nuclei. Around supermassive black holes, The scale expands dramatically while following identical physical principles. Accretion disks can extend across light years, containing more mass than entire star clusters while maintaining the same basic spiral structure and temperature gradient. The innermost regions still reach millions of degrees despite the black hole's vastly larger size, because the gravitational potential energy per unit mass remains comparable for matter orbiting near the event horizon regardless of the black hole's total mass. Only took a few thousand years for the first accretion disks to establish their characteristic structure and begin radiating energy across the electromagnetic spectrum. From radio waves generated by synchrotron emission to X-rays produced by thermal radiation from the hottest inner regions, the spectrum carries detailed information about physical conditions within the disk, temperature, density, magnetic field strength, and chemical composition, encoded in absorption and emission lines that astronomers can decipher like cosmic hieroglyphs. The magnetic fields threading through these early accretion disks arise from dynamo processes that amplify weak seed fields through the differential rotation between inner and outer disk regions, just as Earth's magnetic field emerges from convection currents in the liquid iron core. Accretion disk magnetic fields grow through magnetorotational instabilities that convert rotational energy into magnetic energy with efficiencies approaching 10%, far higher than any nuclear reaction. These magnetic fields do more than provide turbulent viscosity for angular momentum transport. They also launch powerful jets of relativistic particles along the rotation axis of the black hole, creating bipolar outflows that can extend across thousands of light years while carrying away significant fractions of the total energy released through gravitational accretion. The jet formation mechanism remains one of astrophysics' most elegant mysteries, involving the extraction of rotational energy from the black hole itself through frame-dragging effects predicted by general relativity. Theoretical models suggest that rotating black holes can act like cosmic flywheels, storing rotational energy that magnetic field lines can tap through the Blandford-Znajek mechanism, a process where magnetic field lines threading the ergosphere become twisted by frame dragging and accelerate charged particles to relativistic speeds. This allows black holes to power jets even when accretion rates remain low, turning gravitational energy into kinetic energy of outflowing plasma with remarkable efficiency. The accretion process operates through a delicate balance between inward gravitational forces and outward pressure gradients that depend sensitively on the rate at which matter approaches the black hole. When accretion rates remain below the Eddington limit, the disk maintains a thin, geometrically stable configuration where radiation pressure remains subordinate to gas pressure and magnetic pressure. The disk radiates efficiently, converting roughly 10% of the infalling rest mass energy into electromagnetic radiation. But when matter falls toward the black hole faster than the Eddington rate, radiation pressure begins dominating the disk dynamics, inflating the accretion flow into thick, geometrically unstable configurations that can actually reduce the efficiency of energy conversion. These super-Eddington flows may have been common during the universe's youth, when gas densities remained high and galaxy merger rates frequently triggered massive inflow episodes that overwhelmed the self-regulating feedback mechanisms. The chemical evolution of accretion disk material follows pathways that mirror stellar nucleosynthesis, but operate under radically different physical conditions. Temperatures in the inner disk regions can exceed those found in stellar cores, hot enough to photodisintegrate heavy nuclei back into protons and neutrons, then rebuild them through rapid neutron capture processes that create isotopes impossible to form in normal stellar environments. Some theoretical models propose that accretion disks around the first black holes served as cosmic foundries for heavy element production, forging rare isotopes through neutron flux densities that exceeded those achievable in any stellar environment. The disk material, enriched with these heavy elements, eventually gets expelled through winds and jets, seeding the surrounding interstellar medium with metals that will be incorporated into the next generation of stars and planetary systems. The radiation emitted by these early accretion disks contributes to the universe's second phase of reionization, following the initial ionization caused by the first generation of massive stars. Unlike stellar ultraviolet radiation, which primarily affects hydrogen, the hard X-ray and gamma-ray emission from black hole accretion can penetrate much deeper into neutral gas clouds, heating and ionizing material across vast volumes of space that stellar radiation cannot reach. This creates a feedback loop where black hole growth influences the thermal and ionization state of the intergalactic medium, which in turn affects the rate at which matter can cool and condense onto black holes and their host galaxies. The interplay between black hole accretion and cosmological structure formation operates across multiple scales simultaneously, from the microscopic physics of plasma instabilities to the macroscopic dynamics of galaxy formation and evolution. Computer simulations reveal that accretion onto the first black holes likely proceeded in highly variable, episodic fashion rather than the steady flows assumed in simplified theoretical models. Gravitational interactions with nearby stars, gas clouds, or other black holes can disrupt accretion flows, causing dramatic changes in luminosity over timescales ranging from hours to thousands of years. These variability patterns provide another observational signature that future space-based telescopes might detect from the universe's earliest epochs. The disk instabilities that drive this variability arise from the fundamental magnetohydrodynamic processes that govern plasma behavior in strong gravitational and magnetic fields. Spiral density waves propagate through the disk material like ripples on a pond, carrying angular momentum outward and triggering episodes of enhanced accretion that can temporarily increase the black hole's luminosity by factors of hundreds or thousands above its quiescent level. The sound waves and shock fronts propagating through accretion disk material create acoustic oscillations that modulate the disk's emission across all wavelengths, from radio to gamma rays. These oscillations carry information about the disk's internal structure and the black hole's mass and rotation rate encoded in their frequency spectra, providing a form of asteroseismology for black hole systems that operates analogously to the study of stellar interiors through solar oscillations. Only took a few million years for the first accretion disks to establish the fundamental patterns of black hole feeding that will persist throughout cosmic history, creating the template for quasar activity, galactic jets, and the complex feedback processes that regulate star formation in galaxies across the universe. The cosmic irony echoes through deep time. These invisible gravitational monsters announce their presence through the brightest, most energetic phenomena the universe has ever produced, transforming their own growth into beacons visible across billions of light-years of expanding space. Deep in the cosmic web's filamentary structure, two black holes begin a gravitational dance that will span millions of years before culminating in the universe's most violent merger event. These objects, perhaps formed from the deaths of the first massive stars or grown through early accretion episodes, spiral toward each other through a cosmic choreography governed by Einstein's general theory of relativity, a dance that literally warps the fabric of space-time itself with each orbital revolution. The initial separation might span hundreds of astronomical units, distances comparable to the outer reaches of planetary systems, with orbital periods measured in thousands of years. At such vast separations, the black holes interact primarily through Newtonian gravity, following elliptical orbits that slowly decay as gravitational wave radiation carries away orbital energy at rates so infinitesimal they would be undetectable by any conceivable instrument. The energy loss occurs through space-time curvature itself. The accelerating masses create ripples in the metric of space and time that propagate outward at the speed of light, carrying momentum and energy away from the binary system. As the orbit decays over cosmic time, the black holes gradually spiral closer together, their orbital period decreasing according to precise mathematical relationships derived from Einstein's field equations. The gravitational wave luminosity, the rate of energy loss through space-time distortion, increases dramatically as the separation decreases. Following a power law that accelerates the inspiral process, what begins as an almost imperceptibly slow orbital decay eventually becomes a runaway process that concludes with merger in a fraction of a second. The inspiral phase follows predictable patterns that depend only on the masses and initial orbital parameters of the two black holes, creating gravitational wave signatures that encode detailed information about the merging objects. Lower mass binaries complete more orbital cycles during their final approach, producing longer duration signals with characteristic frequency sweeps that rise from millihertz to kilohertz over time scales ranging from minutes to milliseconds. For black holes with masses comparable to those formed from the first generation of stars, perhaps tens to hundreds of solar masses each, the final inspiral unfolds over several minutes of cosmic time while producing gravitational waves that sweep upward through the frequency band accessible to ground-based detectors. The amplitude of these space-time ripples grows steadily as the black holes approach each other, reaching maximum strength during the final few milliseconds before merger when orbital velocities approach significant fractions of the speed of light. The mathematics governing this process emerge from some of the most beautiful equations in theoretical physics, combining general relativity's geometric description of gravity with post-Newtonian approximation methods that account for relativistic corrections to orbital motion. The energy radiated in gravitational waves follows Stefan Boltzmann-type scaling laws, where the luminosity increases as the fourth power of the orbital frequency, creating exponential growth in energy loss rates as the black holes approach their final merger. During the last few orbital cycles, when the black holes orbit each other every few milliseconds while separated by distances comparable to their own event horizon radii, relativistic effects dominate the dynamics completely. Frame dragging caused by the rotating space-time around each black hole affects the orbital precession, while tidal deformations of the event horizons themselves begin influencing the gravitational wave emission pattern in ways that depend on the individual black hole spins and their alignment with the orbital angular momentum. The merger itself represents a moment of profound geometric transformation where two separate event horizons coalesce into a single, larger horizon that initially oscillates violently before settling into the equilibrium shape predicted by black hole thermodynamics. This process, lasting perhaps a few milliseconds in total, releases more energy in gravitational waves than all the stars in the observable universe emit in electromagnetic radiation during the same time interval. Only took a fraction of a second for the actual merger process to convert several solar masses worth of material energy directly into gravitational wave radiation, creating the most luminous events in the universe when measured by total power output across all forms of energy emission. The peak gravitational wave luminosity can exceed the electromagnetic luminosity of all stars and galaxies within the observable horizon by factors of thousands. Though this energy couples only weakly to ordinary matter and propagates invisibly through space at the speed of light, the newly formed black hole emerges from this cosmic collision in a highly distorted, rapidly rotating state that must shed excess energy and angular momentum through continued gravitational wave emission. The post-merger ring-down phase follows exponentially decaying oscillation patterns determined by the black hole's final mass and spin, producing gravitational wave frequencies and damping times that depend on the fundamental mode structure predicted by black hole perturbation theory. These ring-down oscillations provide direct observational access to the emergent black hole's intrinsic properties, mass, spin, and electric charge, through frequency analysis of the decaying gravitational wave signal. The oscillation frequencies correspond to the black hole's quasi-normal modes, analogous to the way a struck bell rings with characteristic overtones determined by its size. composition, and shape. Except that black hole, quasi-normal modes emerge from pure space-time geometry rather than material properties. The gravitational waves produced during these primordial mergers propagate across the universe at the speed of light, carrying information about the merger event encoded in the amplitude and phase evolution of the space-time strain. Unlike electromagnetic radiation, gravitational waves interact only weakly with intervening matter, allowing them to traverse the cosmos essentially unimpeded by gas, dust, or any other material that might obscure optical or radio observations. This creates a unique window into the universe's earliest epochs, since gravitational waves from black hole mergers during cosmic dawn can reach modern detectors carrying pristine information about conditions when the universe was only a few 100 million years old. The wave strain amplitude decreases inversely with distance from the source, but the fundamental waveform shape remains unaltered by propagation through the expanding universe. Aside from cosmological redshift effects that stretch the signal to lower frequencies, the cosmic expansion itself affects gravitational wave propagation in subtle but measurable ways that provide independent constraints on cosmological parameters. The redshift of gravitational wave frequencies follows the same 1 plus z scaling as electromagnetic radiation, where z represents the cosmological redshift parameter, but gravitational waves also carry information about luminosity distance through their amplitude, allowing direct measurement of the Hubble constant and other cosmological parameters without relying on the cosmic distance ladder. Advanced theoretical models predict that the universe's first black hole mergers occurred at redshifts exceeding z equals sine 10, corresponding to cosmic times less than 500 million years after the Big Bang. These primordial merger events would produce gravitational wave signatures redshifted to frequencies below the sensitivity band of current ground-based detectors, requiring next-generation space-based interferometers to observe directly. The merger rate during the universe's youth remains highly uncertain, depending sensitively on the formation mechanisms for the first black holes and the subsequent evolution of their host dark matter halos. Computer simulations suggest that binary black hole formation rates could have been much higher during cosmic dawn due to the higher gas densities and more frequent galaxy mergers that characterized early cosmic structure formation. Some theoretical scenarios predict that primordial black hole mergers could have contributed significantly to the stochastic gravitational wave background, a persistent, isotropic signal arising from the superposition of countless unresolved merger events throughout cosmic history. This background would carry statistical information about black hole formation rates, mass distributions, and merger dynamics across all cosmic epochs from the present back to the earliest times when black holes could form. The detection of primordial gravitational waves would provide unprecedented insight into physical processes operating during the universe's dark ages, the period between cosmic recombination and the formation of the first stars, when electromagnetic observations cannot penetrate the neutral hydrogen that filled space. Gravitational waves from this epoch would reveal the assembly history of the first gravitationally bound structures and the rates at which they underwent violent merger processes. Modern gravitational wave observatories like LIGO and Virgo have begun detecting merger events from the recent universe, confirming Einstein's predictions about space-time dynamics and opening an entirely new observational window onto cosmic phenomena. Each detection provides direct evidence for black hole existence while testing general relativity under the most extreme conditions of strong gravitational fields and high-velocity motion achievable in nature. The gravitational wave signals carry encoded information about fundamental physics that cannot be accessed through any other observational method. The propagation speed of gravitational waves provides direct tests of general relativity's prediction that gravitational influences travel at exactly the speed of light. Deviations from this prediction would indicate new physics beyond Einstein's theory, such as massive gravitons or extraspatial dimensions predicted by some quantum gravity theories. Only took the universe a few billion years to establish the population of merging black hole binaries that will continue producing gravitational wave signals throughout the remainder of cosmic history, creating a persistent background of space-time distortions that carry information about structure formation and gravitational dynamics across all cosmic scales and epochs. The cosmic irony resonates across deep time. These most violent events in nature produce signals so gentle they barely disturb the atoms in gravitational wave detectors, yet carry more energy than the nuclear fusion powering billions of stars. Even as these violent mergers shake the fabric of space-time, the universe's black holes harbor a more subtle process that will ultimately determine their fate across vast spans of cosmic time. Quantum mechanics, operating at the intersection of general relativity and particle physics, predicts that black holes cannot remain perfectly black but must instead emit thermal radiation. Through a process so counterintuitive, it challenged the fundamental assumptions of 20th century physics when Stephen Hawking first derived it in 1974. The mechanism emerges from quantum field theory in curved spacetime, where the violent tidal forces near a black hole's event horizon create particle-antiparticle pairs from the vacuum energy that permeates all of space under normal circumstances. These virtual particles annihilate each other almost instantaneously, contributing only to the zero-point energy of quantum fields. But near an event horizon, the extreme spacetime curvature can separate these particle pairs before annihilation occurs, allowing one member to fall into the black hole while the other escapes to infinity as real radiation. The escaping particles carry positive energy away from the black hole, while the negative energy partners that fall inward reduce the black hole's total mass energy according to Einstein's mass-energy equivalence. This creates a slow but inexorable evaporation process where black holes gradually convert their mass into thermal radiation through purely quantum mechanical effects that operate independently of any classical accretion or merger processes. The temperature of this Hawking radiation proves inversely proportional to the black hole's mass. Following a relationship so precise, it establishes fundamental connections between gravity, quantum mechanics, and thermodynamics. Stellar mass black holes with masses comparable to our Sun maintain temperatures of only 60 nanokelvins, 60 billionths of a degree above absolute zero, making their thermal emission essentially undetectable against the cosmic microwave background radiation that bathes the universe at 2.7 Kelvin. But as black holes lose mass through evaporation, their temperature increases according to the inverse relationship, causing the evaporation rate to accelerate in a runaway process that culminates in explosive energy release during the final moments of black hole existence. A black hole that loses half its mass sees its temperature double, quadrupling the power output and further accelerating the mass loss in a feedback loop that grows exponentially as the remaining mass approaches zero. Only took Stephen Hawking's mathematical analysis to reveal that black holes possess finite lifetimes determined entirely by their initial mass, following scaling laws that span dozens of orders of magnitude in both mass and evaporation time. The relationship follows a cubic power law where evaporation time increases as the cube of the black hole mass, meaning that doubling the mass increases the lifetime eightfold, creating a vast hierarchy of evaporation timescales across the black hole mass spectrum. Primordial black holes with masses comparable to mountains would evaporate completely in times comparable to the current age of the universe, potentially contributing to dark matter or producing observable signatures in high-energy cosmic ray detectors. Stellar mass black holes require evaporation times exceeding 10 circumflex 67 years, unimaginably longer than the current cosmic age of 13. 8 billion years and far beyond any conceivable future epoch when stars might still be forming or galaxies still be merging. Supermassive black holes face evaporation timescales that challenge comprehension even by cosmological standards. A billion solar mass black hole, typical of those found in massive galaxy centers, requires approximately 10 circumflex 98 years to evaporate completely through Hawking radiation, a time span so vast it exceeds the current age of the universe by a factor larger than the number of atoms in the observable cosmos. The quantum field theory underlying Hawking radiation operates through mathematical frameworks that combine general relativity's curved space-time geometry with the canonical quantization procedures of particle physics. The calculation requires evaluating quantum field propagators in the gravitational background of a black hole, taking into account the causal structure imposed by the event horizon and the asymptotic boundary conditions at spatial infinity. Different approaches to the calculation, including the original derivation using Bogoliubov transformations between different vacuum states, the tunneling method based on DWKB approximation techniques, and the anomaly cancellation method using conformal field theory, all yield identical results for the radiation temperature and luminosity, providing strong theoretical confidence in the fundamental correctness of the Hawking effect despite its profound conceptual implications. The thermal nature of Hawking radiation creates deep connections between black hole physics and statistical thermodynamics that extend far beyond the original calculation. Black holes possess entropy proportional to their event horizon area rather than their volume. Following the Bekenstein-Hawking formula that assigns one bit of information to every 4 Planck areas of horizon surface, this area law for black hole entropy suggests fundamental limits on information storage that may reflect the holographic nature of quantum gravity. The spectrum of Hawking radiation follows a perfect blackbody distribution across all frequencies, with no information about the matter that originally formed the black hole or subsequently fell past the event horizon. This creates the black hole information paradox. The question of what happens to quantum information when it falls into a black hole, and whether this information can be recovered when the black hole eventually evaporates through Hawking radiation. Current theoretical research suggests several possible resolutions to the information paradox, ranging from modifications to quantum mechanics itself to subtle correlations in the Hawking radiation that could encode the information of infalling matter in ways too complex to detect with current mathematical techniques. The AD-S-CFT correspondence from string theory provides one framework for understanding how information might be preserved through holographic encoding on the black hole's event horizon. Experimental verification of Hawking radiation remains beyond current technological capabilities for astrophysical black holes, but analog systems in condensed matter physics and atomic gases have demonstrated similar thermal emission from horizon-like boundaries in acoustic and optical systems. These analog experiments confirm the mathematical structure underlying Hawking's calculation while providing laboratory tests of quantum field theory in curved spacetime. The discovery of Hawking radiation fundamentally changed physicists' understanding of black holes from purely classical objects to quantum mechanical systems that obey the laws of thermodynamics. Black holes can be assigned temperatures, entropies, and heat capacities like any other thermodynamic system, though their properties differ qualitatively from ordinary matter in having negative heat capacity. They grow hotter as they lose energy through evaporation. This negative heat capacity creates thermodynamic instability for black holes in thermal equilibrium with external radiation fields. A black hole immersed in radiation warmer than its Hawking temperature will absorb more energy than it radiates, growing larger and cooler. Conversely, a black hole in a cooler environment will radiate more than it absorbs, shrinking and heating up in the runaway evaporation process that eventually leads to complete disappearance. The current cosmic microwave background temperature of 2.7 Kelvin means that only the smallest primordial black holes, those with masses less than about 1/10 the mass of Earth's moon, can evaporate in the present-day universe. all larger black holes continue growing by absorbing cosmic microwave background photons faster than they can emit Hawking radiation, though this growth rate becomes negligible as the universe continues expanding and the background radiation temperature continues falling. Future epochs will witness the gradual transition from a universe dominated by stellar processes and galaxy evolution to one where black hole evaporation becomes the primary source of energy and entropy production. As the cosmic microwave background cools below the Hawking temperature of progressively larger black holes, evaporation will begin dominating over accretion for stellar mass objects first, then intermediate mass black holes, and eventually even the most massive supermassive black holes that currently anchor galactic centers. Only took quantum mechanics and general relativity together to predict this ultimate fate for all black holes in the universe, ensuring that even these most permanent-seeming objects must eventually return their mass energy to the cosmic inventory through thermal radiation processes that operate on timescales vastly exceeding any other physical process in nature. The irony whispers across deep time. The universe's most perfect absorbers of matter and energy will ultimately become its most patient sources of thermal emission, glowing softly in the cosmic dark long after the last stars have exhausted their nuclear fuel and faded into white dwarf remnants cooling toward absolute zero. The gentle whisper of Hawking radiation carries with it one of theoretical physics' most profound puzzles, a paradox that strikes at the heart of our understanding of information. Quantum mechanics, and the nature of reality itself. When matter falls past a black hole's event horizon, it appears to vanish from the observable universe, taking with it all the quantum information that specifies its precise, microscopic state. Yet quantum mechanics insists that information cannot be destroyed, only transformed or redistributed, creating a fundamental tension between black hole physics and the mathematical foundations of quantum theory. The problem emerges most clearly when considering what happens to a quantum system, perhaps a photon with specific polarization, frequency, and phase, that falls into a black hole and becomes part of the black hole's mass energy content. The quantum state of this photon encodes information that, according to the principles of quantum mechanics, must be preserved somewhere in the universe's total quantum state. But general relativity suggests that this information disappears behind the event horizon, becoming causally disconnected from the external universe and ultimately destroyed when the black hole evaporates. Stephen Hawking's original calculation treated the evaporation process as perfectly thermal, producing radiation with a black body spectrum that carries no information about the matter that originally formed the black hole or subsequently fell past the event horizon. This thermal radiation appears to emerge from quantum vacuum fluctuations near the horizon rather than from the interior matter, suggesting that information about infalling particles simply vanishes when the black hole completely evaporates, violating one of quantum mechanics' fundamental conservation laws. The mathematical framework underlying this paradox involves the subtle interplay between quantum field theory and general relativity in regions of extreme space-time curvature. Near an event horizon, the Unruh effect causes accelerated observers to perceive thermal radiation from the quantum vacuum, while freely falling observers detect no such radiation due to their inertial reference frame. This observer-dependent nature of thermal radiation reflects the deep connections between acceleration, gravity, and thermodynamics first recognized in Einstein's equivalence principle. Only took decades of theoretical investigation to reveal that the information paradox represents more than a technical problem in black hole physics. It probes fundamental questions about the nature of space-time, causality, and the relationship between quantum mechanics and gravity that may require revolutionary changes to our understanding of physical reality. The paradox has motivated research programs ranging from string theory to loop quantum gravity, each attempting to resolve the tension through different approaches to quantum gravity. Current theoretical research suggests several possible resolutions, though none has achieved universal acceptance among physicists. The black hole complementarity principle proposes that information both falls into the black hole from the perspective of external observers and emerges in Hawking radiation from the perspective of observers near the horizon. With no single reference frame able to observe both processes simultaneously, this resolution relies on the fundamental observer dependence of quantum measurements in curved space-time. Alternative approaches invoke quantum entanglement between Hawking radiation and the black hole interior, suggesting that information about infalling matter becomes encoded in subtle correlations between outgoing photons that extend across the entire evaporation process. These correlations might be too complex to decode with classical information processing techniques, but they could preserve quantum information in a form accessible to sufficiently sophisticated quantum computers capable of analyzing the complete radiation output. The holographic principle provides another framework for resolving the paradox by suggesting that all information about black hole interior states can be encoded on the event horizon surface according to the holographic bound, one bit of information per Planck area of horizon. This encoding mechanism might allow information to be preserved and eventually recovered through analysis of Hawking radiation patterns, though the specific holographic mapping remains unclear in most approaches to quantum gravity. String theory offers additional possibilities through its description of black holes as collections of D-branes, extended objects that can store and process quantum information through their internal degrees of freedom. In this picture, information falling into a string theory, black hole becomes encoded in the microstates of the D-brane system, preserving quantum information while maintaining consistency with general relativity's geometric description of space-time curvature. Loop quantum gravity approaches the paradox by proposing that space-time itself possesses discrete, quantum mechanical structure at the Planck scale, potentially allowing information to be preserved through quantum geometric degrees of freedom that remain hidden in classical general relativity. The loop quantum gravity description of black hole interiors suggests possibilities for information storage and retrieval that depend on the fundamental quantum nature of spatial geometry. Recent developments in quantum error correction have revealed deep connections between black hole physics and information theory that may illuminate pathways toward paradox resolution. The ARCHIVISTS CFT correspondence demonstrates explicit examples where black hole formation and evaporation in anti-de Sitter spacetime corresponds to unitary quantum evolution in a lower dimensional conformal field theory, proving that information can be preserved in at least some theoretical models of quantum gravity. The firewall paradox represents a more recent refinement of the information puzzle, arising from attempts to preserve quantum information through entanglement between Hawking radiation and black hole interior modes. This approach leads to the prediction that the event horizon should be replaced by a firewall of high-energy radiation that would destroy any observer attempting to fall into the black hole, contradicting general relativity's prediction of smooth passage through the horizon for freely falling observers. Quantum computational approaches to the paradox investigate whether information processing limitations might prevent external observers from extracting quantum information from Hawking radiation even when such information is theoretically present. These studies reveal fundamental connections between black hole physics, computational complexity theory, and the ultimate physical limits on information processing in strongly gravitating systems. The paradox also illuminates deep questions about the nature of time and causality in quantum gravity. Different approaches to quantum gravity, string theory, loop quantum gravity, causal dynamical triangulation, make different predictions about the fate of information falling into black holes, suggesting that resolving the paradox might require selecting among competing theories of quantum spacetime based on their treatment of quantum information. Experimental tests of information paradox resolutions remain far beyond current technological capabilities, since they would require detailed analysis of Hawking radiation from evaporating black holes over timescales vastly exceeding the current age of the universe. However, analog systems using condensed matter or atomic physics might provide laboratory tests of specific aspects of the paradox within controlled quantum systems. The philosophical implications extend beyond physics to questions about the nature of reality, observation, and the role of information in fundamental physical law. If quantum information cannot be destroyed, then black holes must preserve information through mechanisms that transcend classical space-time geometry, suggesting that information itself might be more fundamental than the geometric description of gravity provided by general relativity. Modern approaches increasingly suggest that resolving the information paradox will require abandoning some cherished assumptions about locality, causality, or the independence of quantum measurements from gravitational fields. The paradox may ultimately demonstrate that quantum mechanics and general relativity cannot be reconciled within classical frameworks of space-time and matter, demanding revolutionary advances in our understanding of the relationship between information, geometry, and physical law. Only took the merger of quantum mechanics and general relativity to reveal this profound puzzle about the nature of information and reality, creating a theoretical challenge that continues driving fundamental research in quantum gravity decades after its original formulation. The cosmic irony persists across deep time. Black holes, which appear to be the ultimate destroyers of information, may actually be the universe's most sophisticated information processing systems, encoding and manipulating quantum data through mechanisms that transcend our current understanding of physical possibility. Beyond their role as cosmic mysteries, black holes emerge as the universe's master architects, sculpting the formation and evolution of galaxies through feedback mechanisms so powerful they regulate star birth across volumes millions of times larger than the black holes themselves. These gravitational monsters, despite containing less than 1% of their host galaxy's total mass, exert controlling influence over galactic structure through jets, winds, and radiation fields that can either trigger or suppress star formation across entire galactic disks. The relationship between supermassive black holes and their host galaxies reveals itself through remarkably tight correlations that persist across cosmic time. From the earliest quasars detected at high redshift to massive elliptical galaxies in the local universe. The M-sigma relation, the correlation between black hole mass and the velocity dispersion of stars in the galactic bulge, suggests that black hole growth and galaxy formation proceed through coordinated processes that operate simultaneously across vastly different spatial scales, from the sub-parsec scales of accretion disks to the kiloparsec scales of galactic stellar distributions. This coordination occurs through active galactic nucleus feedback, where energy released during black hole accretion couples to the surrounding interstellar and intergalactic medium through multiple physical channels. Radiation pressure from the accretion disk can drive powerful winds that sweep gas out of the galaxy's gravitational potential well, reducing the fuel available for both continued black hole growth and future star formation. Meanwhile, relativistic jets launched along the black hole's rotation axis can heat the surrounding gas to temperatures exceeding millions of degrees, preventing cooling and condensation into star-forming molecular clouds. The energy scales involved in these feedback processes dwarf those of stellar evolution and supernova explosions. A supermassive black hole accreting at 10% of the Eddington rate releases energy equivalent to 10 million supernovae per year, sustained over timescales of millions to hundreds of millions of years. This energy output exceeds the combined luminosity of all stars in the host galaxy, creating radiation fields intense enough to ionize gas across the entire galactic volume and beyond. The mechanical feedback operates through jets that can extend across hundreds of kiloparsecs, far beyond the visible boundaries of their host galaxies, and into the intergalactic medium that fills the space between galaxies. These jets transport energy and momentum from the central black hole to the galaxy's outer regions and beyond, inflating enormous bubbles of hot plasma that can persist for hundreds of millions of years while preventing gas cooling and subsequent star formation. Only took a few billion years for this feedback cycle to establish the fundamental scaling relationships observed between black holes and galaxies in the modern universe, suggesting that the coordination between black hole growth and stellar mass assembly operates as a self-regulating process. When star formation rates exceed certain thresholds, the increased gas supply feeds the central black hole more rapidly, triggering stronger feedback that suppresses further star formation until the system reaches a quasi-equilibrium state. The physics underlying this self-regulation involves complex interactions between radiative transfer, magnetohydrodynamics, and thermodynamics operating across multiple phases of the interstellar medium. Cold molecular gas provides fuel for star formation, but heating by active galactic nucleus radiation can dissociate molecules and drive turbulence that prevents gravitational collapse into stellar nurseries. Meanwhile, hot ionized gas heated by black hole feedback expands and flows out of the galaxy, carrying away metals produced by stellar nucleosynthesis. Galaxy mergers provide the primary mechanism for triggering the most dramatic episodes of black hole feedback through gravitational torques that drive gas inflows toward galactic centers. When two galaxies collide, tidal forces disrupt stellar orbits and channel gas into the inner regions where it can fuel rapid black hole growth. The resulting quasar phase can outshine the combined stellar luminosity of both merging galaxies while generating feedback so powerful it eventually terminates both star formation and black hole accretion. Computer simulations of galaxy formation reveal that including black hole feedback fundamentally changes the predicted properties of massive galaxies, bringing theoretical models into agreement with observational data for the first time. Without feedback, simulated galaxies form too many stars and grow too massive compared to observed galaxies of similar dark matter halo mass. The inclusion of realistic feedback mechanisms produces galaxy populations that match observations across wide ranges in mass, luminosity, and morphology. The feedback operates differently across different galaxy mass scales, creating a bimodal distribution where low-mass galaxies continue forming stars efficiently while high-mass galaxies experience quenched star formation through active galactic nucleus heating. This mass threshold corresponds to dark matter halo masses around 10 circumflex 12 solar masses, where the virial temperature of infalling gas approaches the temperatures achievable through black hole feedback mechanisms. The cosmic evolution of black hole feedback links directly to the assembly history of dark matter structure in the expanding universe. Early cosmic epochs, when gas densities remained higher and galaxy merger rates more frequent, experienced more violent feedback episodes that carved out large volumes of heated intergalactic medium. Modern epochs witness more gentle feedback from lower luminosity active galactic nuclei that maintain thermal balance in galaxy groups and clusters without completely expelling gas from their gravitational potential wells. Radio mode feedback represents a particularly important mechanism in massive galaxies, where mechanical energy injection through relativistic jets maintains heating rates that balance radiative cooling in hot gaseous halos. This mode operates at relatively low accretion rates but can persist for billions of years, providing steady energy input that prevents cooling catastrophes in massive elliptical galaxies and galaxy clusters. The jet launching mechanism itself involves magnetic field lines threading the black hole ergosphere, extracting rotational energy through the Blandford-Zanarjek process with efficiencies that can approach 40% for rapidly rotating black holes. These jets maintain tight collimation across distances exceeding millions of light years through magnetic pinching effects and interactions with the surrounding medium, creating some of the most tightly focused energy flows known in astrophysics. Environmental effects modulate black hole feedback through the density and temperature of surrounding gas, creating systematic variations in feedback strength between isolated galaxies, galaxy groups, and rich galaxy clusters. Dense cluster environments provide more ambient gas for accretion, but also create stronger ram pressure that can strip gas from galaxy disks, leading to complex feedback cycles that depend on orbital phase and cluster-centric distance. The chemical enrichment of the intergalactic medium proceeds through the combination of stellar winds, supernova explosions, and black hole-driven outflows that transport heavy elements produced by stellar nucleosynthesis beyond galaxy boundaries. Black hole feedback plays a crucial role in this enrichment by providing the energy necessary to accelerate gas to escape velocities from massive galaxy potential wells, seeding the broader cosmic web with metals that influence subsequent generations of galaxy formation. Modern observations reveal fossil evidence of ancient black hole feedback episodes in the form of X-ray cavities, shock fronts, and metal abundance patterns preserved in the hot gas surrounding massive galaxies and galaxy clusters. These features provide direct evidence for mechanical feedback operating over timescales comparable to the age of the universe, demonstrating the long-term impact of black hole activity on cosmic structure formation. The relationship between black hole mass and host galaxy properties suggests that feedback operates as a cosmic thermostat, maintaining thermal and dynamical equilibrium across galaxy populations through mechanisms that remain actively regulated over cosmic time. This regulation requires a delicate balance between gas cooling, star formation, black hole accretion, and feedback energy injection that somehow maintains itself across billions of years of galactic evolution. Future observations with next-generation telescopes will probe black hole feedback across cosmic time, revealing how the strength and character of feedback mechanisms evolved as the universe expanded and cooled from its denser, more violent youth to the relatively quiescent cosmic environment observed today. These studies will illuminate fundamental questions about the coevolution of black holes and galaxies that shaped the cosmic structure we observe throughout the modern universe. Only took the universe a few billion years to establish feedback mechanisms so precisely calibrated that they regulate galaxy formation across cosmic time while maintaining the tight correlations between black hole and galactic properties that persist from the earliest epochs to the present day. The cosmic irony resonates across deep space. These gravitational monsters that seem to consume everything actually serve as cosmic gardeners, pruning and shaping galactic growth through invisible hands of gravity, magnetism, and radiation that operate across scales from quantum to cosmological. Near these cosmic architects of galactic structure, the familiar flow of time itself begins to stretch and distort according to Einstein's general theory of relativity, creating regions where minutes become hours, hours become years, and the steady tick of cosmic chronometry gives way to temporal landscapes so warped that simultaneity loses all meaning. The gravitational time dilation near black holes represents one of space-time geometry's most profound manifestations, transforming time from a universal constant into a local variable that depends on position within the curved metric surrounding these gravitational monsters. The mathematical description emerges from the Schwarzschild solution to Einstein's field equations, which describes the space-time geometry around a spherically symmetric, non-rotating black hole through a metric tensor that encodes how distances and time intervals transform under the influence of extreme gravity, as observers move closer to the event horizon. The gravitational redshift factor, the ratio between coordinate time measured by distant observers and proper time experienced locally, approaches infinity, causing time dilation effects so severe that finite proper time intervals correspond to infinite coordinate time as measured from far away. The physical mechanism underlying this temporal distortion arises from the equivalence principle, Einstein's insight that gravitational acceleration and kinematic acceleration produce identical local effects on physical processes. An observer hovering at a fixed distance from a black hole must accelerate continuously outward to avoid falling inward. experiencing proper acceleration that increases without bound as the event horizon approaches. This acceleration produces time dilation effects identical to those experienced by observers undergoing constant acceleration in flat spacetime, but amplified to extreme values by the black hole's gravitational field strength. At distances far from the black hole, time dilation effects remain negligible, with clocks running essentially at the same rate as they would in empty space. But as the gravitational potential deepens closer to the event horizon, time dilation becomes increasingly pronounced, following mathematical relationships that depend on the precise space-time metric around the black hole. For Schwarzschild black holes, the time dilation factor equals the reciprocal of the square root of 1 minus the ratio of the Schwarzschild radius to the observer's coordinate radius. Only took Einstein's geometric theory of gravity to predict that massive objects fundamentally alter the rate of time's passage, transforming temporal flow from absolute universality to local relativity that depends on gravitational field strength and observer motion. Near stellar mass black holes, an observer hovering just outside the event horizon experiences time dilation so severe that 1 second of local proper time corresponds to years or decades of coordinate time measured by distant observers watching the process unfold. The extreme time dilation creates apparent paradoxes for observers trying to understand black hole formation and evolution from different reference frames. An external observer watching matter fall toward a black hole sees the infalling material slow down and redshift as it approaches the event horizon, with the image becoming increasingly dim and red as time dilation stretches the light's wavelength toward infrared and radio frequencies. The infalling matter appears to freeze at the horizon, taking infinite coordinate time to actually cross the boundary. But from the perspective of the freely falling observer, the journey proceeds normally according to local clocks, with passage through the event horizon occurring in finite proper time without any locally detectable boundary or barrier. The falling observer experiences normal passage of time until reaching the central singularity, where tidal forces become infinite and the known laws of physics break down. These dramatically different descriptions of the same physical process reflect the observer-dependent nature of space-time measurements in general relativity. The rotating Kerr black holes that likely dominate in nature introduce additional complexity through frame-dragging effects that twist space-time around the rotating mass, creating regions where the distinction between space and time coordinates becomes blurred. Near a rapidly rotating black hole, the dragging of space-time can become so severe that maintaining a fixed spatial position relative to distant stars requires orbital motion around the black hole, demonstrating how rotation couples to the metric structure of curved space-time. The ergosphere, the region outside the event horizon where frame-dragging effects become dominant, represents a zone where time and space coordinates exchange roles in the mathematical description of the metric. Observers within the ergosphere cannot remain stationary relative to distant stars, but must orbit the black hole in the same direction as its rotation, carried along by the twisted geometry of space-time itself. Extreme time dilation near black holes creates possibilities for time travel paradoxes and closed time-like curves that challenge our understanding of causality and the logical structure of physical law. In principle, an observer could orbit close to a rotating black hole for what feels like a short time locally, then return to distant regions to find that much longer periods have elapsed there, effectively traveling into the future through gravitational time dilation rather than high-speed motion. The observational signatures of extreme time dilation appear in the spectra and variability patterns of matter orbiting close to black holes, where the finite light travel time combined with gravitational time dilation creates complex delay patterns and frequency shifts that depend on orbital phase and emission region. X-ray reverberation mapping uses these time delay signatures to probe the space-time geometry near black holes with precision approaching that required to test general relativity in the strong field regime. Atomic clocks placed at different distances from black holes would run at detectably different rates, with the differences increasing dramatically as the clocks approach the event horizon. These time dilation effects have been measured experimentally using atomic clocks at different gravitational potentials on Earth's surface, confirming Einstein's predictions with precision exceeding 1 part in 10 circumflex 15 and demonstrating that time dilation represents a real physical effect rather than merely a mathematical curiosity. The global structure of space-time around black holes creates regions where different observers disagree fundamentally about the simultaneity and causal ordering of distant events, demonstrating that the intuitive notion of universal present time breaks down in curved space-time. Events that appear simultaneous to observers far from the black hole occur at different times according to observers closer to the event horizon, reflecting the relative nature of temporal relationships in general relativity. Quantum field theory in curved space-time predicts that time dilation effects near black holes influence particle creation and annihilation processes, contributing to the complex physics underlying Hawking radiation emission from event horizons. The extreme space-time curvature mixes positive and negative frequency modes of quantum fields, creating particle production rates that depend sensitively on the local time dilation factor and its variation with position near the black hole. The combination of time dilation and redshift effects creates observational challenges for studying processes near black holes, since radiation emitted close to the event horizon arrives at distant observers, both delayed and redshifted, by factors that can exceed thousands or millions. High-energy gamma rays emitted near the horizon might be observed as low-energy radio waves that arrive years after their emission, carrying information about physical processes occurring in regions where time itself flows differently than anywhere else in the observable universe. Advanced theoretical models predict that time dilation effects near black holes could influence fundamental physical constants through quantum gravitational corrections that become important when space-time curvature approaches the Planck scale. These effects might modify the rates of atomic transitions, nuclear decay processes, and other fundamental physical phenomena in ways that depend on position within the black hole's gravitational field. The measurement of time itself becomes observer-dependent near black holes, with different observational frames leading to different conclusions about the duration and temporal ordering of physical processes. This relativity of time measurement reflects the deeper truth that space and time form a unified four-dimensional continuum, where gravitational fields determine the local geometry and causal structure through Einstein's field equations. Only took the universe's most extreme gravitational environments to reveal time's fundamental plasticity, demonstrating that temporal flow depends on local space-time geometry rather than representing an absolute backdrop against which physical processes unfold. The cosmic irony echoes through warped space-time. Black holes that seem to trap everything, including light itself, actually demonstrate time's freedom from universal constraints, allowing different regions of space to experience the passage of moments at rates that differ by factors approaching infinity, creating temporal landscapes as varied and complex as the spatial geography of curved four-dimensional space-time. Within these landscapes of warped time, the gravitational fields surrounding black holes exert tidal forces so extreme they can stretch and compress matter in ways that defy everyday experience, creating conditions where the familiar physics of solid bodies gives way to a more fundamental truth, that gravity acts differently on different parts of extended objects, pulling with greater force on regions closer to the gravitational source while exerting weaker attraction on more distant portions of the same system. The mathematical origin of tidal forces emerges from the inverse square law of gravitational attraction combined with the finite size of objects falling toward black holes. While the gravitational acceleration at any specific point depends only on the local field strength, Extended objects experience differential acceleration across their volume because different parts occupy regions where the gravitational field possesses different magnitudes and directions. These differential forces stretch objects along the line, connecting them to the black hole's center while compressing them perpendicular to this direction. Near stellar mass black holes, tidal acceleration gradients become appreciable at distances of several Schwarzschild radii, where the difference in gravitational attraction between an object's head and feet can exceed the material strength of any known substance. A human-sized object falling toward a 10 solar mass black hole would experience tidal stretching forces exceeding the tensile strength of steel when still several kilometers away from the event horizon, demonstrating how black holes can disrupt matter through purely gravitational means long before direct contact occurs. The stretching process follows precise mathematical relationships derived from general relativity's description of space-time curvature, with tidal accelerations scaling as the mass of the black hole divided by the cube of the distance from the center. This means that tidal forces strengthen rapidly as objects fall closer to the event horizon, while also being stronger for less massive black holes at fixed distances due to their more compact size and steeper gravitational gradients. The term spaghettification captures the visual essence of how tidal forces deform falling objects, stretching them into long, thin shapes reminiscent of pasta strands as the gravitational gradient overcomes the electromagnetic and nuclear forces that normally maintain material cohesion. This process occurs gradually at first, with mild stretching that might be imperceptible to the falling observer, but accelerates dramatically as the tidal acceleration approaches and exceeds the structural limits of whatever material comprises the infalling object. Only took general relativity's geometric description of gravity to predict that tidal disruption represents an inevitable fate for extended objects falling into stellar mass black holes, though the precise details depend on the object's size, composition, internal structure, and approach trajectory. Rocky objects like asteroids or planets experience tidal disruption at different distances than gaseous objects like stars, reflecting the different material properties and internal pressure gradients that determine resistance to external deformation. The physics of tidal disruption involves complex interactions between gravitational acceleration gradients and the equation of state that describes how matter responds to applied stress and compression. Materials with higher tensile strength, metals, crystalline solids, degenerate matter, can resist tidal stretching to smaller distances from black holes than softer materials like biological tissue, liquid water, or normal stellar plasma that deform more easily under applied stress. For supermassive black holes with masses millions or billions of times that of our Sun, the situation becomes dramatically different due to the gentler gravitational gradients that result from their larger size. An object falling toward a billion solar mass black hole might cross the event horizon completely intact, experiencing tidal forces no stronger than those created by Earth's gravity, because the event horizon lies so far from the central singularity that gravitational gradients remain mild across human scale dimensions. This scale-dependent nature of tidal effects creates a fascinating paradox. The most massive black holes in the universe, despite their enormous gravitational fields, provide the gentlest passage through their event horizons for infalling observers. A person falling into the supermassive black hole at the center of our galaxy would experience essentially no tidal stretching during passage through the event horizon, though they would still be doomed by the increasing tidal forces encountered during subsequent infall toward the central singularity. The disruption process releases gravitational potential energy as internal kinetic energy within the stretched object, heating the material as gravitational work gets converted to thermal motion of constituent particles. This heating can trigger nuclear reactions, chemical processes, or phase transitions that would not occur under normal conditions, creating exotic states of matter that exist only during the brief intervals when objects undergo extreme tidal deformation. Stellar tidal disruption events represent spectacular astronomical phenomena where entire stars get stretched apart by supermassive black holes, creating luminous flares visible across cosmological distances as the stellar material forms temporary accretion disks before ultimately disappearing past the event horizon. These events provide direct observational evidence for tidal forces operating around black holes, while offering insights into stellar structure and composition through spectroscopic analysis of the disrupted material. The mathematical description of tidal tensor components reveals that gravitational fields can create both stretching and compression simultaneously along different spatial directions. Following the traceless nature of the Riemann curvature tensor in vacuum spacetime, objects falling radially toward black holes experience stretching along the radial direction while being compressed along directions perpendicular to their motion, conserving volume while dramatically changing shape. Advanced general relativistic calculations show that tidal effects near rotating black holes become significantly more complex due to the twisted space-time geometry created by frame dragging. Where the simple radial stretching and circumferential compression of Schwarzschild black holes gives way to shearing motions that can twist falling objects like cosmic corkscrews. The Kerr metric introduces additional tidal components that depend on the black hole's angular momentum, creating differential forces that rotate different parts of extended objects at slightly different rates as they fall through the ergosphere. These rotational tidal effects can induce spin-up of initially non-rotating objects, transferring angular momentum from the black hole's rotation to infalling matter through gravitational coupling mechanisms that operate purely through space-time geometry rather than any direct mechanical contact. The process demonstrates how black holes can influence matter through the curvature properties of four-dimensional space-time, creating torques and angular accelerations that arise from the metric structure itself. The quantum mechanical aspects of tidal disruption involve the breakdown of molecular and atomic bonds when tidal accelerations exceed the electromagnetic forces that hold matter together at microscopic scales. Individual atoms can survive much stronger tidal fields than macroscopic objects because the electromagnetic forces binding electrons to nuclei scale differently with distance than gravitational forces. But even atomic structure eventually succumbs to sufficiently extreme space-time curvature near the central singularity. Computer simulations of stellar tidal disruption reveal complex fluid dynamic processes as stellar material gets stretched into long streams that oscillate, fragment, and interact through self-gravity while orbiting the black hole. These simulations predict observable signatures, including characteristic light curves, spectral evolution, and polarization patterns that depend on the stellar mass, black hole mass, orbital parameters, and viewing angle, providing theoretical frameworks for interpreting observational data from tidal disruption events. The debris from tidally disrupted objects follows complex orbital trajectories that depend on the specific location within the original object where each particle was located at the moment of disruption. Material from the stellar surface follows different orbital paths than material from the stellar core, creating streams with different orbital periods and approach distances that can lead to multiple brightening episodes as different components of the disrupted star return to periapsy passage near the black hole. Tidal heating during the disruption process can trigger nuclear fusion in stellar material that was previously too cool or low density to sustain nuclear reactions, creating temporary fusion episodes that contribute additional energy to the observable electromagnetic emission. This process can produce exotic nucleosynthesis pathways that create isotopic signatures different from normal stellar burning, potentially contributing to the chemical enrichment of surrounding gas with rare nuclear species. The study of tidal forces provides crucial tests of general relativity in the strong field regime, where linear approximations break down and the full, non-linear structure of Einstein's field equations becomes essential for accurate predictions. Precise measurements of tidal disruption event properties can constrain black hole parameters, test alternative theories of gravity, and probe the equation of state of stellar material under extreme conditions impossible to recreate in terrestrial laboratories. Observational surveys searching for tidal disruption events have detected dozens of these spectacular phenomena, revealing a rich diversity of disruption mechanisms, light curve morphologies, and spectral characteristics that depend on the complex interplay between black hole properties, stellar structure, orbital geometry, and environmental conditions. Each detection provides a unique laboratory for studying extreme gravitational physics under conditions that push theoretical models to their limits. The rate of tidal disruption events in galaxies provides statistical information about supermassive black hole demographics, galactic stellar populations, and the dynamical processes that scatter stars into black hole crossing orbits over cosmic time. These rates depend on galaxy morphology, stellar density profiles, binary star populations, and the presence of intermediate mass black holes that can scatter stars towards supermassive black holes through three-body gravitational interactions. Future space-based gravitational wave observatories may detect the gravitational wave signatures of tidal disruption events, providing complementary information about the disruption process through space-time distortions rather than electromagnetic emission. These gravitational wave signals encode information about the object's internal structure, the black hole's mass and spin, and the detailed dynamics of the disruption process that may not be accessible through optical or X-ray observations. The extreme tidal environment near black holes creates conditions where the standard assumptions of continuum mechanics break down and discrete particle effects become important for understanding material behavior. Individual atoms and molecules experience differential acceleration that can overcome intermolecular forces, leading to dissociation and ionization processes that occur through purely gravitational mechanisms rather than thermal or electromagnetic heating. Theoretical models predict that tidal forces can accelerate charged particles to relativistic speeds through gravitational mechanisms alone, creating high-energy radiation through synchrotron emission, inverse Compton scattering, and other non-thermal processes that contribute to the observed spectra of tidal disruption events. These acceleration mechanisms may explain the hard X-ray and gamma-ray emission observed from some disruption events that cannot be accounted for by simple thermal emission models. The long-term evolution of tidal debris depends on complex interactions between self-gravity, pressure gradients, magnetic fields, and radiation forces that determine whether the disrupted material eventually accretes onto the black hole, escapes to infinity, or forms bound structures like temporary accretion disks or stellar remnants. Magnetohydrodynamic effects can become important when the disrupted material possesses magnetic fields that get amplified and tangled during the stretching process. Only took the universe's most extreme gravitational environments to reveal the fundamental limits of material coherence, demonstrating that all forms of matter, from dust grains to planets to stars, ultimately succumb to tidal forces that arise from the basic geometric properties of curved spacetime rather than any specific material properties. The cosmic irony stretches across warped spacetime like the matter it describes. Black holes that seem to consume everything intact actually dismantle their victims piece by piece, atom by atom, through the patient action of differential gravity that treats matter not as solid objects, but as collections of particles, each following its own geodesic path through the curved geometry of four-dimensional spacetime. Beyond the realm of inevitable destruction lies a more subtle possibility: the extraction of energy from black holes themselves through mechanisms that seem to violate the intuitive notion that nothing can escape from these gravitational traps. The Penrose process, first described by mathematical physicist Roger Penrose in 1969, demonstrates how the rotational energy of spinning black holes can be tapped through carefully orchestrated particle interactions that occur within the ergosphere, the region outside the event horizon where space-time itself rotates with the black hole's angular momentum. The ergosphere exists only around rotating black holes, bounded by the event horizon on the inside and the static limit surface on the outside, the boundary where maintaining a fixed position relative to distant stars becomes impossible due to frame-dragging effects. Within this region, space-time curvature becomes so extreme that even light rays pointing directly away from the black hole get dragged forward in the direction of rotation, creating a zone where the normal distinction between space and time coordinates breaks down in the mathematical description of the metric. The energy extraction mechanism operates through a process that initially seems paradoxical by dropping matter into a black hole. Observers can extract more energy than they originally possessed, seemingly violating conservation of energy until the full relativistic accounting reveals that the energy comes from the black hole's rotational kinetic energy rather than being created from nothing. The process requires splitting a particle into two fragments within the ergosphere, with one fragment following a trajectory that carries negative energy and angular momentum into the black hole, while the other escapes to infinity with more energy than the original particle possessed. The mathematical description involves the Kerr metric's peculiar property that certain trajectories within the ergosphere correspond to negative energy as measured by observers at infinity, even though the local energy remains positive for all observers following time-like world lines. This apparent contradiction arises from the fact that energy measurements depend on the choice of time-like killing vector used to define temporal translation symmetry, and the natural choice for asymptotic observers becomes space-like within the ergosphere. Only took Roger Penrose's geometric insight into black hole space-time to reveal that rotating black holes cannot maintain their angular momentum indefinitely when surrounded by matter, but must gradually spin down through interactions that transfer rotational energy to escaping particles while carrying angular momentum into the event horizon through infalling debris. This establishes a fundamental connection between black hole thermodynamics and classical mechanics that operates through purely gravitational interactions. The efficiency of energy extraction through the Penrose process depends on the black hole's dimensionless spin parameter, which ranges from 0 for non-rotating Schwarzschild black holes to unity for maximally rotating Kerr black holes, where the event horizon nearly touches the static limit surface. Higher spin rates create larger ergospheres with more pronounced frame-dragging effects, increasing both the range of possible extraction trajectories and the maximum energy that can be extracted from individual particle interactions. For maximally rotating black holes, the Penrose process can theoretically extract up to 29% of the black hole's rest mass energy, representing the ultimate limit of energy extraction efficiency from any physical system. This exceeds the efficiency of nuclear fusion by factors of hundreds, making rotating black holes the most energy-dense objects in the universe and potential sources of power for advanced civilizations capable of manipulating matter trajectories within ergospheres. The astrophysical implementation of energy extraction occurs naturally through accretion disk processes, where magnetic field lines threading the ergosphere get twisted by frame-dragging effects, extracting rotational energy through electromagnetic rather than purely mechanical means. The Blandford-Znajek mechanism provides a more realistic pathway for energy extraction that operates continuously rather than requiring carefully orchestrated particle trajectories, tapping black hole spin energy through magnetohydrodynamic processes that power the most luminous jets observed in quasars and radio galaxies. The magnetic field configuration required for the Blandford-Znajek process involves field lines that connect the black hole ergosphere to the surrounding accretion disk and extend outward to large distances where the extracted energy can be deposited in relativistic particle beams. The frame-dragging effect twists these magnetic field lines, inducing electric fields that accelerate charged particles along the field lines and extract energy from the black hole's rotation through electromagnetic torques. Computer simulations of magnetized accretion flows around rotating black holes reveal complex three-dimensional magnetic field structures that naturally develop the configurations necessary for efficient energy extraction, suggesting that the Blandford-Znajek mechanism operates routinely in astrophysical environments rather than representing an exotic theoretical possibility. These simulations predict jet powers that scale with black hole spin rate and magnetic field strength in ways that match observational data from active galactic nuclei. The observational signatures of energy extraction through black hole spin include the correlation between jet luminosity and black hole spin rate measured through X-ray spectroscopy of ion emission lines from the inner accretion disk. Rapidly spinning black holes tend to power more luminous jets and exhibit different accretion flow properties than slowly spinning or non-rotating black holes, providing indirect evidence for spin-dependent energy extraction mechanisms operating in nature. Theoretical limits on energy extraction arise from the requirement that the process must respect causality and the second law of thermodynamics even in curved spacetime, preventing unlimited energy extraction that would violate fundamental physical principles. The irreducible mass of a black hole, the minimum possible mass for a black hole with given electric charge, sets absolute limits on how much energy can be extracted before the extraction process itself becomes impossible. The cosmic evolution of black hole spins depends on the balance between spin-up through coherent accretion and spin-down through energy extraction processes, chaotic accretion episodes, and gravitational wave emission during black hole mergers. Observational surveys of black hole spin rates provide statistical information about these competing processes and their relative importance during different epochs of cosmic structure formation. Advanced theoretical models predict that primordial black holes formed through direct collapse mechanisms might possess near maximal spin rates due to the angular momentum of the collapsing gas clouds, making them efficient sources of energy extraction if they exist in nature. These rapidly spinning primordial black holes could power exotic high-energy phenomena during the universe's earliest epochs, while gradually spinning down through energy extraction processes operating over cosmic time. The quantum mechanical aspects of energy extraction involve the modification of Hawking radiation emission rates and spectra for rotating black holes, where the frame-dragging effects influence particle creation processes near the event horizon in ways that depend on the black hole's angular momentum. The superradiant amplification of quantum fields can extract rotational energy even from black holes in vacuum, demonstrating that energy extraction represents a fundamental property of rotating black holes rather than merely an astrophysical curiosity. Laboratory analog systems using fluid vortices, acoustic waves in moving media, and electromagnetic fields in rotating dielectric materials have demonstrated superradiant amplification and energy extraction mechanisms that operate according to the same mathematical principles as the Penrose process, providing experimental verification of the underlying physics in controlled terrestrial environments where the effects can be measured with conventional instruments. The engineering challenges of implementing controlled energy extraction from astrophysical black holes include the difficulty of manipulating matter trajectories within ergospheres, the extreme radiation environments near accreting black holes, and the vast distances between potential energy extraction sites and locations where the extracted energy could be utilized. These challenges may explain why advanced extraterrestrial civilizations have not already harvested energy from supermassive black holes on scales that would be detectable through astronomical observations. Future space-based experiments might test energy extraction principles using small-scale analog systems or precision measurements of frame-dragging effects around rapidly rotating dense objects, providing laboratory verification of general relativistic predictions about energy extraction from rotating spacetimes. These experiments could illuminate fundamental questions about the relationship between geometry, rotation, and energy in curved spacetime, while testing the theoretical foundations underlying proposed energy extraction mechanisms, only took the geometric properties of rotating spacetime to reveal that black holes need not be perfect absorbers, but can serve as cosmic engines capable of converting their own rotational energy into usable power through processes that operate at the intersection of general relativity, thermodynamics, and electromagnetism. The cosmic irony spins through curved spacetime with mathematical precision. These ultimate gravitational traps become potential energy sources through the very rotation that makes them more efficient at capturing matter, demonstrating that even the universe's most perfect prisons contain keys to their own exploitation hidden within the elegant geometry of Einstein's field equations. Within the mathematical landscape of general relativity lies perhaps the most speculative yet captivating possibility that black holes might serve not merely as cosmic endpoints, but as gateways to other regions of space-time, connected through hypothetical structures known as wormholes, bridges that could theoretically link distant parts of our universe, or even provide passages to entirely different cosmic domains separated by dimensions we cannot directly perceive or traverse through conventional means. The theoretical foundation for these space-time tunnels emerges from exact solutions to Einstein's field equations, particularly the maximally extended Schwarzschild geometry that describes the complete space-time manifold around an eternal black hole. This mathematical construction reveals that black hole interiors connect to white hole regions through a bridge-like structure in four-dimensional space-time, creating a topology where matter could theoretically enter through the black hole and emerge from the white hole in a different region of space or time. The Einstein-Rosen bridge, first described in 1935 by Albert Einstein and Nathan Rosen, represents the simplest example of such space-time connections, arising naturally from the mathematical requirement that Schwarzschild spacetime be geodesically complete, meaning that freely falling particles can continue their trajectories indefinitely without encountering artificial boundaries in the space-time manifold. This completeness condition forces the inclusion of regions that lie beyond both the black hole and white hole event horizons, connected through a throat that represents the narrowest part of the wormhole bridge. The geometry of these theoretical passages defies intuitive understanding, creating regions where the normal relationship between spatial distance and travel time breaks down completely. Two events that appear separated by millions of light years when measured through ordinary three-dimensional space might be connected by a wormhole throat spanning only a few kilometers, potentially allowing faster-than-light communication or travel through curved spacetime rather than motion through flat space at superluminal velocities. Only took the mathematical machinery of general relativity to reveal that space-time topology need not conform to the simple connectivity assumptions of everyday experience, opening theoretical possibilities for non-trivial geometric structures that could dramatically alter the relationship between cause and effect, locality and non-locality, and the fundamental limitations imposed by the speed of light on information transmission across cosmic distances. However, detailed analysis of wormhole solutions reveals fundamental instabilities that prevent their natural occurrence or stable maintenance in realistic astrophysical environments. The throat of an Einstein-Rosen bridge pinches off faster than light can traverse the connection, making traversal impossible for any physical object or signal. This instability arises from the focusing properties of gravity, which naturally tends to converge geodesics and create singularities rather than maintain open pathways through spacetime. Keeping wormholes open for traversal requires exotic matter with negative energy density, material that violates the weak energy condition by possessing stress energy tensor eigenvalues that remain negative in all reference frames. Such matter would exert gravitational repulsion rather than attraction, creating the outward pressure necessary to hold wormhole throats open against the natural tendency of space-time geometry to develop focusing singularities under the influence of ordinary matter fields. The quantum field theory of curved spacetime provides potential sources of negative energy through phenomena like the Casimir effect, where quantum vacuum fluctuations between conducting plates create measurably negative energy densities that could theoretically stabilize wormhole geometries on microscopic scales. However, scaling these quantum effects to macroscopic wormhole sizes would require negative energy quantities that vastly exceed anything achievable through known physical processes. Advanced theoretical models explore the possibility that quantum corrections to classical general relativity might naturally create stable wormhole structures during the universe's earliest moments, when energy densities approached the Planck scale and quantum gravitational effects dominated space-time dynamics. These primordial wormholes could potentially survive to the present epoch as microscopic structures that might be detectable through their gravitational lensing effects or influence on particle physics processes. String theory and other approaches to quantum gravity predict the existence of higher dimensional spaces where our familiar four-dimensional space-time represents a lower dimensional surface or brane embedded within a larger geometric structure. In these models, wormholes might exist as connections between different branes or different regions of the higher dimensional space, potentially providing pathways for information or energy transfer that bypass the limitations imposed by four-dimensional general relativity. The observational signatures of macroscopic wormholes would include distinctive gravitational lensing patterns, unique spectroscopic features from matter falling into wormhole mouths, and potentially detectable gravitational wave emissions from the exotic matter required to maintain their stability. Current astronomical surveys have not detected any phenomena that require wormhole explanations, suggesting that such structures either do not exist in nature or remain too small or rare to produce observable effects. Microscopic wormholes operating at quantum scales might influence particle physics through virtual processes that connect distant regions of space-time, potentially contributing to quantum entanglement phenomena or providing mechanisms for information transmission that could circumvent the classical limitations imposed by light-speed communication. These quantum wormholes would exist only briefly as virtual fluctuations in space-time geometry before collapsing back into the vacuum state. The relationship between wormholes and black hole interiors remains an active area of theoretical research, with some models suggesting that the interiors of black holes might be connected through wormhole-like structures that preserve information and maintain consistency with quantum mechanics. The ER=EPR conjecture proposes that quantum entanglement and space-time bridges represent different descriptions of the same underlying physical phenomena. Computer simulations of wormhole dynamics reveal complex interactions between exotic matter, stress energy, and space-time curvature that determine whether particular wormhole geometries remain stable or collapse on timescales short compared to light crossing times. These simulations suggest that maintaining stable traversable wormholes requires continuous monitoring and adjustment of exotic matter distributions to counteract perturbations that naturally develop through interactions with ordinary matter and radiation fields. The engineering challenges of constructing artificial wormholes include the production and manipulation of exotic matter in sufficient quantities to create macroscopic space-time bridges, the development of control mechanisms that can maintain wormhole stability against perturbations, and the design of entry and exit procedures that allow safe passage through regions of extreme space-time curvature without lethal tidal effects. Advanced civilizations with access to technologies based on quantum gravity or extra-dimensional physics might theoretically construct stable wormhole networks that enable rapid transportation and communication across galactic distances, though the energy requirements and technical challenges would likely exceed any conceivable engineering capabilities for billions of years of technological development. The philosophical implications of traversable wormholes extend to fundamental questions about causality, free will, and the nature of physical law. Since wormhole travel could potentially allow closed time-like curves that enable effects to precede their causes in ways that create logical paradoxes. The resolution of these paradoxes might require modifications to quantum mechanics. General relativity, or our understanding of the relationship between information and physical processes. Laboratory experiments studying analog wormhole systems in condensed matter physics, acoustic metamaterials, and electromagnetic waveguides provide insights into the basic physics of space-time bridges while avoiding the exotic matter requirements of gravitational wormholes. These analog systems demonstrate that wormhole-like connections can exist and remain stable in certain physical contexts. Though they do not directly test the gravitational aspects of Einstein-Rosen bridge physics, the search for observational evidence of wormholes continues through surveys that monitor gravitational lensing anomalies, unusual stellar motions near galactic centers, and high-energy particle interactions that might reveal signatures of extra-dimensional or non-trivial space-time topology. Negative results from these searches place increasingly stringent limits on the abundance and properties of any wormhole structures that might exist in nature. Future developments in quantum gravity theory, observational astronomy, and high-energy physics may ultimately determine whether wormholes represent merely mathematical curiosities arising from the formal structure of general relativity or genuine physical phenomena that could revolutionize our understanding of space-time connectivity and the ultimate limits on transportation and communication across cosmic distances. Only took the mathematical formalism of Einstein's field equations to reveal the theoretical possibility that space-time itself might possess a topology more complex than simple connectivity, creating potential bridges between distant regions that challenge our assumptions about the relationship between geometry and physics, while remaining tantalizingly beyond experimental verification or practical implementation. The cosmic irony threads through curved space-time like the mathematical structures it describes. These ultimate shortcuts through the universe remain forever theoretical, demonstrating how mathematics can reveal possibilities that nature may choose never to implement. The mathematical elegance of black hole physics reaches perhaps its most profound expression in the discovery that these gravitational monsters obey the same fundamental thermodynamic laws that govern steam engines, refrigerators, and all other systems that exchange energy and entropy with their surroundings. This revelation, emerging from the intersection of general relativity, quantum mechanics, and statistical physics, transforms black holes from purely geometric objects described by Einstein's field equations into thermodynamic entities with temperature, entropy, and heat capacity that follow precise mathematical relationships analogous to those governing ordinary matter. The first hint of black hole thermodynamics appeared in Jacob Bekenstein's insight that black holes must possess entropy to prevent violations of the second law of thermodynamics when matter with known entropy falls past an event horizon. If black holes carried no entropy, the total entropy of the universe would decrease whenever organized matter disappeared into these gravitational traps, violating one of physics' most fundamental principles about the irreversible increase of disorder in isolated systems. Bekenstein proposed that black hole entropy should be proportional to the area of the event horizon rather than the volume enclosed within it, following a relationship that assigns exactly one bit of information to every 4 square Planck lengths of horizon surface. This area law represents a profound departure from ordinary thermodynamic systems, where entropy typically scales with volume and reflects the number of microscopic configurations available to the system's constituent particles. The Bekenstein-Hawking entropy formula, S equals A divided by 4 times the Planck length squared, establishes a direct connection between the geometric properties of space-time curvature and the information theoretic concepts that underlie statistical mechanics. The formula suggests that event horizons serve as fundamental information storage devices, encoding data about infalling matter in ways that remain accessible through the geometric properties of the horizon surface itself. Only took the mathematical machinery of quantum field theory in curved spacetime to reveal that black holes must possess finite temperature through the Hawking radiation emission process, where virtual particle pairs near the event horizon become real particles through spacetime curvature effects that separate them before mutual annihilation can occur. The radiation spectrum follows a perfect thermal distribution with temperature inversely proportional to the black hole mass, creating a direct link between gravitational and thermodynamic properties. The temperature relationship: T equals Planck temperature times Planck mass divided by 8 pi times the black hole mass, demonstrates that more massive black holes maintain lower temperatures, while smaller black holes burn hotter through their quantum evaporation process. This inverse relationship creates negative heat capacity, where black holes grow hotter as they lose energy through Hawking radiation, representing thermodynamic behavior opposite to that of ordinary matter systems. The 4 laws of black hole thermodynamics mirror the fundamental laws of ordinary thermodynamics with remarkable precision, suggesting deep connections between gravitational physics and statistical mechanics that transcend the specific mathematical formulations of either theory. The 0th law states that the surface gravity remains constant across the event horizon of a stationary black hole, analogous to thermal equilibrium requiring uniform temperature throughout a system. The 1st law of black hole thermodynamics relates changes in black hole mass to changes in area, angular momentum, and electric charge through an equation that resembles the 1st law of ordinary thermodynamics for systems capable of doing mechanical work while exchanging heat with their surroundings. The temperature and entropy terms appear naturally in this energy balance equation, confirming the thermodynamic interpretation of black hole properties. The 2nd law requires that the total area of all event horizons in any physical process can never decrease, providing a gravitational analog to entropy increase that operates through space-time geometry rather than statistical mechanics of microscopic constituents. This area theorem, first proved by Stephen Hawking using purely classical general relativity, anticipated the entropy interpretation by several years and continues to hold even when quantum effects are included. The 3rd law suggests that it might be impossible to reduce a black hole's temperature to absolute zero through any finite sequence of physical processes, analogous to the impossibility of reaching zero temperature for ordinary thermodynamic systems. This law remains less well established than the others and connects to unresolved questions about extremal black holes and the cosmic censorship hypothesis in general relativity. Computer simulations of black hole formation and evolution demonstrate that these thermodynamic laws emerge naturally from the dynamics of matter and space-time during gravitational collapse, black hole mergers, and accretion processes, suggesting that thermodynamic behavior represents an intrinsic property of black hole spacetimes rather than merely a mathematical analogy to ordinary thermal systems. The microscopic origin of black hole entropy remains one of theoretical physics' most profound puzzles, since black holes appear to have no internal constituents or microscopic degrees of freedom that could account for their enormous entropy values through conventional statistical mechanical counting procedures. String theory provides one approach to this counting problem by modeling black holes as bound states of fundamental strings and d-branes whose quantum states can be enumerated microscopically. Loop quantum gravity offers an alternative microscopic foundation through the discrete geometric degrees of freedom associated with quantum spacetime at the Planck scale, where the area quantization of surfaces in the quantum geometry naturally reproduces the Bekenstein-Hawking entropy formula through counting of surface quantum states that contribute to the horizon area. The holographic principle emerges naturally from black hole thermodynamics by suggesting that all information contained within a spatial volume can be encoded on the boundary surface of that volume, with the encoding density limited by the Bekenstein-Hawking bound of 1 bit per 4 Planck areas. This principle has profound implications for quantum gravity and the fundamental nature of space-time and matter. Experimental tests of black hole thermodynamics remain limited by the impossibly long timescales required for stellar mass black holes to emit detectable Hawking radiation. But analog systems in condensed matter physics, acoustics, and optics demonstrate thermodynamic behavior consistent with theoretical predictions for horizon physics in curved space-time geometries. The connection between black hole thermodynamics and quantum information theory reveals fundamental limits on information processing, storage, and transmission in strongly gravitating systems, where the interplay between quantum mechanics and general relativity creates new constraints on computational processes that operate near event horizons or in regions of extreme space-time curvature. Advanced theoretical models suggest that black hole thermodynamics might provide crucial insights into the fundamental nature of space-time, matter, and information at the deepest levels of physical reality, where the distinction between geometry and thermodynamics dissolves into more fundamental principles that govern the quantum structure of space-time itself. The statistical mechanical interpretation of black hole entropy through microscopic quantum states remains an active frontier in theoretical physics, with different approaches to quantum gravity making different predictions about the detailed structure of these microstates and their relationship to classical space-time geometry and thermodynamic properties. Future developments in quantum gravity theory, observational astronomy, and analog experiments may ultimately reveal whether black hole thermodynamics represents merely a mathematical coincidence or a profound truth about the fundamental relationship between information, geometry, and physical law that applies throughout the universe at scales from microscopic to cosmological. The measurement of black hole thermodynamic properties through gravitational wave observations, X-ray spectroscopy, and other astronomical techniques provides increasingly precise tests of theoretical predictions while opening new windows onto the quantum mechanical nature of space-time in regions where classical general relativity approaches its limits of validity and quantum corrections become important. Only took the synthesis of quantum mechanics, general relativity, and thermodynamics to reveal that black holes obey universal physical laws that transcend the specific mathematical formulations of any single theory, suggesting deep unification principles that may underlie all physical phenomena throughout the cosmos. The cosmic irony resonates through curved space-time with mathematical precision. These regions of ultimate gravitational collapse, where classical physics breaks down, become the testing grounds for the most fundamental laws that govern energy, information, and entropy across all scales of physical reality, from quantum to cosmological. In the cosmic present, 13 billion years after the universe's first black holes formed from the deaths of massive stars and direct collapse of primordial gas clouds, these gravitational relics continue their patient existence in a universe that has grown progressively less dense, less violent, and less conducive to the dramatic accretion episodes that characterized cosmic dawn. The supermassive black holes that anchor modern galaxies maintain their vigil as cosmic time flows onward, growing slowly through occasional stellar disruption events and the gradual consumption of gas clouds that venture too close to their event horizons. The modern universe provides a far different environment for black hole evolution than the dense, gas-rich cosmos of earlier epochs, when galaxy merger rates remained high and accretion disks blazed as luminous quasars that outshone their host galaxies by factors of thousands. Today's intergalactic medium has been heated and enriched by billions of years of stellar evolution, supernova explosions, and active galactic nucleus feedback, creating a more tenuous and higher entropy environment where dramatic accretion episodes occur less frequently. Stellar mass black holes drift through galactic disks and halos like cosmic ghosts, invisible except when they interact gravitationally with nearby stars or accrete material from binary companions through Roche lobe, overflow, or stellar wind capture. These systems provide the only direct observational access to black hole properties in the modern universe, revealing their presence through X-ray emission from heated accretion flows, gravitational lensing of background starlight, and the orbital dynamics of visible stellar companions. The demographics of the black hole population reflect billions of years of cosmic evolution, with mass functions, spin distributions, and spatial locations determined by the complex interplay between star formation history, stellar evolution, galactic dynamics, and merger processes operating across cosmic time. Gravitational wave observations have begun revealing the properties of black hole binaries that remained hidden throughout electromagnetic astronomy, opening new windows onto populations that evolved in isolation for billions of years. Only took 13 billion years of cosmic evolution to establish the modern black hole population that will dominate the universe's future, with growth rates now limited primarily by the availability of fuel rather than the efficiency of accretion processes or the strength of feedback mechanisms that regulated earlier epochs. The transition from active to quiescent phases reflects the universe's overall evolution toward lower density and higher entropy states. Supermassive black holes in modern galaxy centers maintain complex relationships with their host stellar populations through feedback processes that continue operating at reduced intensity compared to earlier cosmic epochs. The correlation between black hole mass and bulge properties suggests ongoing coevolution mechanisms, though the growth rates have slowed dramatically as gas supplies become depleted and galaxy merger rates decline with cosmic expansion. The chemical composition of modern accretion flows reflects billions of years of stellar nucleosynthesis and galactic chemical evolution, with metallicities orders of magnitude higher than the pristine hydrogen and helium that fueled the first generation of black holes. This metal enrichment affects accretion flow physics through enhanced cooling, opacity changes, and dust formation processes that alter the efficiency of angular momentum transport and energy dissipation. Intermediate mass black holes remain among the most elusive objects in modern astronomy, with their existence inferred primarily through indirect evidence from globular cluster dynamics, ultraluminous X-ray sources, and gravitational wave detections that suggest masses between stellar and supermassive scales. These objects may represent surviving remnants of the black hole seeds that formed during cosmic dawn, evolved through complex accretion and merger histories. The observational signatures of modern black hole activity span the entire electromagnetic spectrum, from radio emission generated by synchrotron radiation in relativistic jets to gamma-ray emission from inverse Compton scattering and nuclear processes in accretion disk coronae. Multi-wavelength astronomy provides increasingly detailed views of black hole environments, revealing the complex physics of magnetized plasma under extreme gravitational and electromagnetic conditions. Computer simulations of modern black hole accretion incorporate sophisticated magnetohydrodynamics, radiation transport, and general relativistic effects to model the complex flows that develop around black holes in low-density environments where radiative cooling, magnetic reconnection, and turbulent mixing create highly structured accretion patterns that differ qualitatively from simple steady-state disk models. The spin evolution of modern black holes reflects the cumulative effects of accretion history, with coherent accretion episodes spinning black holes up toward maximum rotation rates, while chaotic accretion and merger events can reduce spin through angular momentum cancellation. Observations of ion line profiles in X-ray spectra provide direct measurements of black hole spin that constrain theoretical models of accretion flow physics and black hole formation mechanisms. Environmental effects continue shaping black hole evolution through interactions with stellar populations, dark matter distributions, and larger-scale structure formation processes that determine gas supply rates, merger frequencies, and the probability of close encounters with other compact objects. Galaxy clusters provide particularly rich environments where black hole interactions occur more frequently than in isolated field galaxies. The search for primordial black holes in the modern universe continues through gravitational wave astronomy, microlensing surveys, and cosmic ray observations that could reveal signatures of black holes formed during the universe's earliest moments rather than through stellar evolution or direct collapse mechanisms. These searches constrain both primordial black hole abundances and the properties of the early universe inflation process. Advanced theoretical models predict that modern black holes will continue evolving through accretion, mergers and Hawking, evaporation over timescales that vastly exceed the current age of the universe, with their ultimate fate determined by the long-term evolution of cosmic structure, the properties of dark energy, and the fundamental physics governing quantum gravity at energy scales approaching the Planck scale. Gravitational wave interferometry has transformed black hole astronomy by providing direct access to strong field gravitational physics, binary evolution in isolation from electromagnetic interactions, and populations of black holes that remained invisible throughout the history of optical and radio astronomy. Each detection provides precision tests of general relativity while revealing new aspects of black hole formation and evolution. The role of magnetic fields in modern black hole physics extends from microscopic plasma processes that govern angular momentum transport in accretion disks to macroscopic jet launching mechanisms that can transport energy across galactic distances while maintaining remarkable collimation and stability over millions of years of propagation through complex, time-varying environments. Future observational capabilities will probe black hole physics through direct imaging of event horizon shadows, precision astrometry of stellar orbits in strong gravitational fields, and gravitational wave astronomy sensitive to black hole mergers across cosmic time. These observations will test fundamental physics while revealing how black holes shaped cosmic structure formation from the earliest epochs to the present day. The modern understanding of black holes as astrophysical objects represents a triumph of theoretical physics validated through observational astronomy, revealing these gravitational monsters to be fundamental components of cosmic structure that influence galaxy evolution, regulate star formation, and provide the most extreme laboratories for testing physical law under conditions of strong gravity. Intense magnetic fields and relativistic motion that cannot be replicated in terrestrial experiments. Contemporary research continues uncovering new aspects of black hole physics through advances in numerical relativity that enable precise modeling of black hole mergers, magnetohydrodynamic simulations that reveal the complex dynamics of accretion flows and jet formation, and observational techniques that probe space-time curvature through gravitational lensing, stellar dynamics, and direct imaging of emission regions near event horizons. The integration of black hole physics with broader astrophysical contexts demonstrates how these objects participate in cosmic recycling processes that redistribute matter and energy across galactic scales, while contributing to chemical enrichment through mechanisms that remain poorly understood but may involve exotic nucleosynthesis in accretion disk environments or jet-driven shock processing of interstellar material. Climate models of galactic evolution increasingly recognize black hole feedback as essential for explaining observed galaxy properties, star formation rates, and the bimodal distribution of galaxy types that divides the cosmic population into actively star-forming spiral galaxies and quiescent elliptical systems where black hole heating maintains thermal balance in hot, gaseous halos. The statistical properties of modern black hole populations encode information about cosmic structure formation, stellar initial mass functions, binary evolution pathways, and dynamical processes operating in dense stellar environments where three-body interactions can modify binary orbits and trigger gravitational wave emission events detectable across cosmological distances. Educational outreach and public engagement with black hole science continue expanding through advances in visualization technology. Gravitational wave astronomy that makes space-time curvature audible through sonification techniques, and theoretical developments that connect black hole physics to fundamental questions about information, causality, and the nature of physical reality that capture broad intellectual interest. The philosophical implications of modern black hole physics extend to questions about the ultimate fate of information in the universe, the relationship between geometry and thermodynamics, the foundations of quantum mechanics in curved spacetime, and the possibility that black holes provide windows into quantum gravity phenomena that could revolutionize our understanding of space, time, and matter at the deepest levels. International collaborations in black hole research span theoretical physics, computational modeling, observational astronomy, and gravitational wave detection through projects that coordinate efforts across multiple continents and diverse scientific disciplines, united by shared interests in understanding these most extreme objects and the physical processes they reveal about fundamental natural law. The technological spin-offs from black hole research include advances in precision measurement techniques, data analysis algorithms for extracting weak signals from noisy backgrounds, computational methods for solving complex differential equations, and detector technologies that push the boundaries of mechanical isolation, quantum noise reduction, and interferometric sensing beyond previous limits. Modern black holes continue their cosmic existence as patient witnesses to the universe's ongoing evolution, maintaining their presence as gravitational anchors around which stellar orbits remain bound across billions of years while the cosmos expands, cools, and evolves toward future epochs where these dark sentinels may represent the most long-lived structures surviving from humanity's cosmic neighborhood. Only took the universe 13 billion years to evolve from its first primitive black holes born in cosmic dawn to the sophisticated population of gravitational monsters that anchor modern galaxies, regulate cosmic structure formation, and provide ongoing laboratories for fundamental physics research that continues revealing new aspects of reality through mathematical precision and observational sophistication that grows more refined with each passing decade of scientific progress. The cosmic irony persists across deep time with mathematical elegance. These ultimate products of gravitational collapse that seem to represent endings actually serve as beginnings for new phases of cosmic evolution, new understanding of physical law, and new appreciation for the mathematical beauty that underlies natural phenomena across scales from quantum mechanical to cosmological, demonstrating how the universe's most extreme objects illuminate fundamental truths about reality itself. In the far future, when the last red dwarf stars have exhausted their nuclear fuel and faded to cooling white dwarf remnants, when proton decay has dissolved the atomic nuclei that once comprised planets and asteroids, when the cosmic microwave background has cooled to temperatures measured in nanokelvin rather than the current 7 Kelvin. Black holes will remain as the universe's final residence, patient, unchanging, gradually evaporating through Hawking radiation into a cosmos grown dark, cold, and unimaginably vast through exponential expansion driven by dark energy. The timescales involved in this ultimate cosmic denouement stretch beyond human comprehension, requiring scientific notation with exponents that themselves require exponential notation to express. Stellar mass black holes will persist for approximately 10 circumflex 67 years before completely evaporating, while supermassive black holes with masses billions of times that of our Sun will continue radiating for periods approaching 10 circumflex 100 years, durations so vast they dwarf the current age of the universe by factors larger than the number of atoms currently contained within the observable cosmic horizon. During these unimaginable epochs, the universe will undergo transformation so profound that the current cosmic environment, filled with galaxies, stars, planets, and the complex chemistry that enables life, will seem like a brief, flickering moment in cosmic history. A temporary organizational phase before entropy claims final victory through the patient operation of thermodynamic processes operating across scales from quantum to cosmological. The evaporation process will proceed with mathematical precision according to the inverse relationship between black hole mass and Hawking temperature, creating a runaway feedback mechanism where mass loss accelerates as the remaining black hole grows smaller and hotter. The final moments of each black hole's existence will release energy equivalent to millions of hydrogen bomb explosions compressed into intervals measured in Planck times, creating brief fireworks displays in a cosmos otherwise empty except for elementary particles, photons, and the occasional gravitational wave ripple propagating through space-time at the speed of light. Only took the mathematical framework of quantum field theory in curved space-time to predict this ultimate fate for every black hole in the universe, ensuring that even these most permanent-seeming structures must eventually succumb to the same thermodynamic principles that govern all physical processes from molecular motion to galactic evolution. The universe's final equilibrium state will consist of elementary particles spread so thinly through expanding space that typical separations exceed the current size of galactic superclusters. The intermediate stages of cosmic evolution leading to this heat death will witness fascinating transitions as different black hole mass scales reach their evaporation temperatures in sequence determined by their initial masses and accretion histories. Primordial black holes with masses comparable to asteroids will evaporate first, potentially contributing observable signatures to high-energy cosmic ray fluxes or dark matter detection experiments during humanity's current cosmic epoch. Stellar mass black holes will begin their final evaporation phase when the cosmic microwave background cools below their Hawking temperatures, marking the transition from slow growth through photon absorption to steady mass loss through thermal radiation emission. This transition will occur when the universe has expanded and cooled for approximately 10 circumflex 19 years, roughly a billion times longer than the current cosmic age since the Big Bang. The evaporation proceeds through quantum mechanical processes that operate independently of classical gravitational physics, demonstrating how quantum mechanics ultimately dominates over general relativity in determining the fate of black holes, despite gravity's role in their initial formation and subsequent evolution. The Hawking radiation spectrum carries no information about the internal structure or formation history of the evaporating black hole, emerging as perfect thermal radiation indistinguishable from blackbody emission. Computer simulations of black hole evaporation reveal complex relationships between quantum field theory, space-time curvature, and thermodynamic processes that continue challenging theoretical physicists' understanding of fundamental physics at the intersection of quantum mechanics and gravity. The information paradox remains unresolved, raising profound questions about the fate of quantum information when black holes completely evaporate through Hawking radiation emission. The final epoch of cosmic evolution, dominated by black hole evaporation rather than stellar processes or galactic dynamics, will witness the universe's transition from a gravitationally structured cosmos filled with bound systems to a thermodynamically equilibrated state where entropy reaches its maximum possible value and further evolution becomes impossible except through quantum fluctuations operating across unimaginably vast timescales. Advanced theoretical models suggest that even after all black holes evaporate completely, the universe may continue evolving through quantum tunneling processes that could nucleate new inflationary domains, create virtual particle fluctuations that occasionally condense into macroscopic structures, or undergo phase transitions that fundamentally alter the nature of space. Time. and matter according to principles beyond current physical understanding. The philosophical implications of ultimate cosmic heat death through black hole evaporation extend to fundamental questions about the meaning of existence, the purpose of complexity and consciousness in a universe destined for maximum entropy, and the possibility that cyclical cosmological models might avoid final equilibrium through mechanisms that remain speculative but mathematically consistent with known physical law. Future cosmological observations may constrain the parameters governing cosmic evolution toward heat death by measuring the equation of state of dark energy, the stability of protons and other elementary particles, the properties of quantum vacuum fluctuations, and the relationship between quantum mechanics and gravity that determines black hole thermodynamics and information processing capabilities. The contrast between current cosmic abundance, billions of galaxies containing trillions of stars surrounded by potentially habitable planets, and the ultimate fate of universal thermal equilibrium populated only by elementary particles and occasional quantum fluctuations provides perspective on humanity's place in cosmic history and the temporary nature of all organized structures in an expanding universe. Scientific research into black hole evaporation continues advancing through theoretical developments in quantum gravity, experimental studies of analog systems that mimic horizon physics in laboratory environments, and observational programs that search for signatures of primordial black holes or other exotic objects that might reveal aspects of fundamental physics relevant to understanding ultimate cosmic evolution. The mathematics underlying black hole thermodynamics and evaporation demonstrates remarkable connections between apparently disparate areas of physics: general relativity, quantum field theory, statistical mechanics, information theory, suggesting that understanding cosmic heat death requires synthesis across all fundamental physical theories rather than specialization in any single theoretical framework. Educational implications of cosmic heat death through black hole evaporation include opportunities to explore deep connections between physics and philosophy, mathematics and meaning, scientific understanding and human purpose that arise when contemplating the ultimate fate of complexity and consciousness in an evolving universe governed by precise mathematical laws that permit temporary organization but demand eventual equilibrium. Only took the combination of Einstein's geometric theory of gravity and Hawking's quantum mechanical analysis of curved spacetime to reveal that the universe's most permanent-seeming objects must eventually fade away through thermal radiation, ensuring that cosmic evolution continues beyond stellar death, galactic collision, and proton decay toward a final state of maximum entropy where black holes themselves become memories encoded in the statistical properties of elementary particles dispersed throughout infinitely expanding space. The ultimate cosmic irony whispers across deep time through mathematical equations that span from quantum mechanics to general relativity. These black holes that began as the universe's first gravitational monsters, that shaped galactic evolution across billions of years, that provided laboratories for testing fundamental physics under extreme conditions, will end as the cosmos's final sources of energy and complexity before entropy claims ultimate victory and the universe settles into eternal equilibrium, patient, dark, and silent, except for the gentle whisper of quantum fluctuations operating across timescales that dwarf the entire history of stars, galaxies, and life itself. The cosmic symphony draws toward its gentlest movement, where the universe settles into rhythms so slow they transcend the measurement of time itself. Black holes, those patient architects of cosmic structure, continue their quiet work across spans of years that stretch beyond counting, beyond comprehension, beyond the very concepts of beginning and ending that define human experience of temporal flow. In this deepest of cosmic times, the mathematics that govern reality reveal their most elegant truth, that even the universe's most permanent residents must eventually return to the quantum foam from which all existence emerged. The Hawking radiation whispers its thermal song across frequencies so low they blend into the background hum of expanding space-time, carrying away the last organized energy from regions where matter once danced in complex orbital patterns around gravitational wells deeper than imagination could fathom. The event horizons that once marked absolute boundaries between known and unknowable slowly shrink through quantum mechanical processes, so gentle they barely disturb the vacuum fluctuations that permeate all of space. Each emitted photon carries with it an infinitesimal portion of black hole mass energy. Following quantum field equations that operate with the patience of geological processes but the inevitability of mathematical truth. Space-time itself participates in this final unwinding, its curvature gradually relaxing toward the flat geometry of empty space as the sources of gravitational field weaken through evaporation and disperse through cosmic expansion. The elegant dance between matter and geometry that Einstein's field equations describe reaches its most serene expression in this epoch, where change occurs so slowly it approaches the eternal stillness that may represent the universe's ultimate destination. The cosmic web of dark matter and baryonic structure, once threaded with filaments connecting galaxy clusters across hundreds of millions of light-years, grows ever more tenuous as expansion stretches distances and entropy redistributes energy into increasingly uniform configurations. The complex hierarchical architecture that characterized cosmic dawn gives way to simplicity measured in statistical mechanics rather than gravitational dynamics. In these quiet moments that span geological ages, the universe demonstrates its most profound teaching, that complexity represents a temporary flowering of organizational possibility within the broader context of thermodynamic evolution toward equilibrium. The black holes that once seemed eternal prove as transient as the stars that birthed them, the galaxies that harbored them, and the conscious observers who studied them with wonder and mathematical precision. The final Hawking photons escape into cosmic darkness, carrying no memory of the spectacular events that created their parent black holes billions of years earlier. No trace remains of stellar collapse, galactic mergers, or accretion disk symphonies that once outshone entire galaxy clusters. The universe returns to simplicity through processes so patient they make mountains seem hasty and oceans appear restless. And in this ultimate quietude, where quantum fluctuations represent the most energetic processes still operating across cosmic scales, space-time itself settles into the deepest possible rest, not the rest of endings, but the rest of mathematical equilibrium, where all potentials have been realized and all gradients have been resolved into perfect uniformity. The cosmic story that began with quantum fluctuations in the primordial vacuum returns to quantum fluctuations in an expanded vacuum, having explored every possible intermediate state that physical law permits, black holes in their formation and evaporation. Trace the complete arc of this cosmic narrative from complexity to simplicity, from organization to equilibrium, from the dramatic to the serene. Sleep well, Cosmos, sleep well.